Hello and welcome to Sleepy Science. Tonight, the ground beneath you will stop feeling quite so familiar. Below the quiet streets, sleeping forests, and dark oceans lies a planet that is still moving, cooling, breaking, and rebuilding itself. A world of metal hotter than the surface of the sun. Mountains buried thousands of kilometers below, ancient water locked inside stone, and living organisms surviving where sunlight has never existed. Earth has frozen almost completely, reversed its magnetic poles, erased nearly every species that ever lived, and repeatedly destroyed the landscapes it created. Even now, continents are drifting toward future collisions. The atmosphere is slowly escaping into space, the moon is moving away, and the length of each day is quietly changing. Across 100 unsettling discoveries, we will explore the hidden forces beneath your feet, the forgotten worlds preserved in rock, the strange life concealed under oceans and continents, and the distant future waiting for this planet. Before we begin, tell me where you are listening from, and don't forget to like and subscribe. Now, settle in, let the surface grow quiet, and follow me into the Earth you were never meant to see. Earth's inner core is almost as hot as the surface of the sun. Far beneath the quiet ground beneath your feet lies a place where iron is heated to temperatures that would destroy almost any material at the surface. Scientists estimate that Earth's inner core may reach somewhere between roughly 3,700 and 6,000 degrees Celsius, meaning its hottest estimates are comparable to the visible surface of the sun, which is about 5,500 degrees Celsius. Yet the inner core is not a vast ball of molten metal. It is solid. This apparent contradiction reveals something important about matter. Temperature alone does not decide whether a substance melts. At Earth's center, the weight of the entire planet presses inward from every direction, creating pressure millions of times greater than the air around you. Under that crushing force, iron atoms are held so tightly together that they remain arranged in a solid structure, even while vibrating with extraordinary energy. Surrounding this solid sphere is the liquid outer core, where the pressure is slightly lower, and the mixture of iron, nickel, and lighter elements can flow. No instrument has ever reached either region, so scientists estimate their conditions by recreating immense pressures in laboratories, studying how iron behaves when compressed and heated, and comparing those results with evidence from the planet itself. Much of this internal heat is ancient, left from Earth's violent formation, when countless objects collided and the young planet separated into layers. Additional heat has been released as the inner core slowly crystallizes, while radioactive elements in Earth's rocky interior continue to decay. The result is a planet that appears cool and settled from the outside, but still carries part of its earliest fire within it. You may experience Earth as solid land, calm soil, and familiar stone, yet thousands of kilometers below you, matter exists under conditions closer to a star than to anything you could touch. The inner core quietly reminds you that a world does not need to look alive to remain active, and that beneath the stable surface of ordinary life, the planet is still slowly releasing the heat of its own creation. Humanity has barely scratched the surface of the planet. The deepest hole humanity has ever drilled would disappear almost completely if Earth were reduced to the size of a large globe. On Russia's Kola Peninsula, scientists spent years drilling the Kola super-deep borehole until it reached about 12.26 kilometers beneath the surface, an extraordinary engineering achievement that remains the deepest vertical borehole ever created. But Earth's average radius is approximately 6,371 kilometers, so that record-breaking hole traveled less than 0.2% of the distance towards the planet's center. It did not reach the mantle. It did not come close to the core. It penetrated only a small portion of the continental crust, the thin outer layer on which nearly all human history has unfolded. As the drill descended, temperatures rose higher than engineers had expected. Equipment became increasingly difficult to operate, and the surrounding rock behaved less like a perfectly rigid wall and more like material capable of slowly deforming under heat and pressure. Eventually, the technical challenge became too great. This means almost everything scientists know about Earth's deep interior has been learned without directly visiting it. Earthquake waves travel through the planet and change speed, direction, or disappear depending on the material they cross. Gravity measurements reveal differences in density. The magnetic field provides evidence of moving conductive metal below. Laboratory machines squeeze minerals under enormous pressure, while volcanic eruptions and rare diamonds occasionally carry tiny samples upward from depths that drilling cannot approach. From these scattered clues, scientists have reconstructed the crust, mantle, liquid outer core, and solid inner core, much as someone might understand a locked building by listening to echoes through its walls. The picture is powerful, but it is still indirect, and details continue to change as measurements improve. You have seen photographs from the surfaces of the Moon and Mars, yet no human being has physically traveled even through Earth's crust. The planet beneath you is therefore not a fully explored home, but an immense hidden territory, and the ground you call the bottom of your world is, in reality, only its outermost beginning. Earth may store vast amounts of water inside its minerals. An enormous reserve of water may exist hundreds of kilometers beneath you, but it would look nothing like an underground sea. There are no open caverns filled with waves, no dark ocean waiting beneath the crust, and no hidden shoreline near the mantle. Instead, the water is stored inside minerals, with hydrogen and oxygen held within their crystal structures, in forms often described as hydroxyl. Between about 410 and 660 kilometers below the surface lies the mantle transition zone, where intense pressure transforms familiar mantle minerals into denser forms known as wadsleyite and ringwoodite. These minerals can incorporate significant amounts of water without appearing wet. One of the strongest pieces of direct evidence arrived inside a diamond brought upward from great depth. Trapped within it was a microscopic piece of ringwoodite containing water, showing that at least some regions of the transition zone are genuinely hydrated. Experiments suggest that wadsleyite and ringwoodite have the capacity to store water amounting to a few % of their weight. Because the transition zone surrounds the entire planet and contains an immense quantity of rock, even a small average concentration could represent a reservoir comparable in scale to the oceans at the surface. But the word could matters. Scientists do not yet know how evenly the water is distributed, how full these minerals are globally, or whether estimates from one region apply everywhere. Some areas may be relatively wet, while others may be much drier. This hidden water is also not permanently trapped. Oceanic plates carry hydrated rock downward at subduction zones. Deep minerals exchange water as pressure changes, and volcanic activity can eventually return part of it toward the surface. Earth's oceans may therefore be connected to a slow internal water cycle operating over millions of years. The water in a wave, a cloud, or a glass may belong to a much larger planetary system, passing between the surface and the deep interior through processes too slow for you to witness. What appears to be a blue planet covered by water may also be a world that carries part of its water invisibly within stone, as though the solid Earth itself has learned how to remember the sea. Hidden mountain ranges may rise deep inside Earth. Imagine a mountain range taller than anything on the surface, hidden where the rocky mantle meets Earth's metallic core, and known only through the faint echoes of earthquakes. Scientists have detected irregular structures near the core mantle boundary, almost 2,900 kilometers below your feet, where seismic waves suddenly slow as they pass through unusual material. These features are called ultra-low velocity zones, and some appear to be only a few kilometers high, while others may rise for tens of kilometers, giving them dimensions comparable to enormous buried mountains. They are not mountain ranges in the familiar sense, with cliffs, snow, or open valleys. Instead, they are dense, chemically unusual regions resting against the core, shaped by differences in temperature and composition. One leading explanation is that some of this material began as ancient oceanic crust. After being forced downward at subduction zones, It may have spent hundreds of millions of years sinking through the mantle before collecting near the base of the planet's rocky interior. Other regions may contain partially melted rock or material altered by intense contact with the core. Scientists map these hidden formations by comparing how seismic waves arrive at instruments after traveling through deep Earth, almost as though they were using sound to feel the outline of a landscape that can never be illuminated. Less than the entire core mantle boundary has been examined in detail, so its true geography remains uncertain, and the deepest terrain on Earth may be far more varied than current maps suggest. Above you, mountains are slowly worn down by rain, wind, and ice, but below you may stand another kind of landscape, untouched by sunlight and measured not by human footsteps, but by vibrations passing through the planet. Earth's greatest unseen heights may therefore exist not beneath the sky, but beside its core, reminding you that even the word down can lead toward a world with its own vast and unfamiliar geography. Earth's inner core may rotate differently from the planet above it. At the center of the spinning Earth, one part of the planet may quietly drift out of step with everything you see around you. The inner core is surrounded by the liquid outer core, so it is not rigidly attached to the mantle and crust above it, allowing it to rotate slightly faster or slower relative to the rest of the planet. Scientists cannot watch this motion directly, so they search for earthquakes that occur in nearly the same location years apart. Because the seismic waves from these repeating earthquakes follow almost identical routes through Earth, small changes in their arrival times and wave shapes can reveal whether the inner core has shifted between the two events. Decades of observation suggest that its relative rotation is not constant. A major 2024 study found evidence that the inner core moved slightly ahead of the mantle during part of the early 2000s, then changed its relative motion and slowly traveled back across a similar path after about 2008. This does not mean the inner core suddenly stopped spinning while the rest of Earth continued around it, nor does it mean it began racing backward through space. The difference is extremely small and is measured relative to the rotating surface, more like one moving part of a clock gradually gaining and losing a fraction of a step against another. The causes are still being investigated, but forces associated with motion in the liquid outer core and gravitational coupling with uneven structures in the mantle may gently accelerate or resist the inner core over time. Some researchers also debate whether part of the changing seismic signal could come from deformation near the inner core's surface rather than rotation alone, so the story is still developing. Yet even this uncertainty teaches something remarkable. Earth does not turn as one perfectly unified object. Its deepest layers can exchange momentum and shift against one another across years and decades. While the ground seems to carry you through every day as a single stable platform, the planet's hidden center may be keeping a slightly different rhythm, revealing that even Earth's rotation contains motions nested inside motions. The ground beneath you is broken into plates that never stop moving. The pavement beneath your feet feels motionless only because you are traveling with it. Earth's rigid outer shell, known as the lithosphere, is divided into a collection of enormous tectonic plates made from the crust and the uppermost solid mantle. These plates fit together across the planet, but they are not fixed in place. Measurements made with satellites and ground-based instruments show that they move relative to one another at rates ranging from less than a centimeter to more than 10 centimeters each year. That is usually too slow for your senses to notice. Yet over a human lifetime, the movement can amount to several meters. The plates do not drift across a global ocean of liquid magma, as they are sometimes pictured. Beneath them lies hotter mantle rock that is mostly solid, but can bend and flow gradually over long periods, allowing the rigid surface plates to change position. Their movement is driven by several connected processes rather than one simple motor. Cold, dense edges of plates can sink and pull the rest of a plate behind them. Elevated regions can help push material away, and slow circulation within the mantle can influence the direction of travel. Where plates meet, they may move apart, press together, or slide sideways, concentrating enormous forces along narrow boundaries. Modern instruments can measure this motion before any dramatic event occurs, showing that tectonic activity is not something that begins only when the ground shakes. It is happening continuously, even during the quietest night, across oceans, beneath cities, and under landscapes that appear unchanged for generations. Human beings naturally treat stillness as the normal condition of the ground, but geology reveals the opposite. Stillness is only what extremely slow movement looks like from the perspective of a brief life. You are not standing on an unchanging foundation. You are being carried across the surface by one moving fragment of a planet whose outer shell has never truly learned how to remain still. Earth's magnetic poles have reversed hundreds of times. A compass carried into Earth's distant past would sometimes point in the direction you now call south. The planet's magnetic polarity has reversed hundreds of times, exchanging magnetic north and south without turning Earth upside down or shifting its geographic poles. Scientists discovered this history because cooling lava and accumulating sediments can preserve the direction of the magnetic field that existed when they formed. When researchers examine layers of rock from different ages, they find alternating magnetic signatures, creating a fragmented archive of planetary reversals. These events do not follow a reliable schedule. Millions of years may pass with no complete reversal, while other periods contain several in relatively quick succession. The most recent full reversal occurred about 780,000 years ago, and the transition probably unfolded over hundreds or thousands of years, rather than in a single catastrophic moment. During such a change, the magnetic field would likely weaken and become more complicated, with several temporary magnetic poles appearing before a new dominant orientation emerged. It would not simply switch off, and there is no convincing evidence that previous reversals caused mass extinctions. Humans would nevertheless face challenges that ancient species never encountered, because satellites, navigation systems, electrical infrastructure, and spacecraft can be affected by increased exposure to energetic particles when magnetic protection is reduced. A reversal is also not considered overdue because the intervals between past events have varied enormously, and present changes cannot reliably predict when the next one will begin. The rocks beneath landscapes and oceans therefore preserve a strange truth. The direction that seems permanently written into every compass is only the planet's current arrangement. North has not always been north, and the invisible order guiding travelers today is part of a much longer history in which Earth repeatedly reorganized its magnetic identity. A strange weak zone in Earth's magnetic field is expanding. Satellites passing above part of South America and the southern Atlantic enter a region where Earth's magnetic protection develops an unusual dent. Known as the South Atlantic anomaly, this broad weak zone allows energetic particles trapped around the planet to approach closer to low Earth orbit than they normally would. People standing beneath it are not exposed to a sudden beam of dangerous radiation, and the anomaly produces no obvious effect in daily life at the surface. For spacecraft, however, the difference matters. Sensitive instruments can experience false signals, temporary malfunctions, corrupted data, or damage when they pass through the region. So some satellite operators shut down vulnerable systems before entering it. Observations and magnetic field models covering the years from 2015 through 2025 show that the anomaly has been drifting westward, weakening in intensity and spreading across a larger area. Its weakest region has also developed two distinct lobes, making the shape more complex than a single smooth depression. This feature exists partly because Earth's magnetic axis is not perfectly aligned with its rotational axis, but deeper irregularities also contribute. In particular, a region of magnetic influence beneath southern Africa appears to oppose part of the planet's dominant field, weakening the total field measured above the Atlantic. Scientists watch the anomaly because its movement offers a rare way to study slow changes occurring far below the surface, but they caution against treating it as proof that a global pole reversal is beginning. Magnetic fields naturally contain local variations, and one expanding weak region does not reveal the future of the entire system. Still, the anomaly changes the way you might imagine Earth's protection. The magnetic field is not a flawless shell of equal strength surrounding the planet. It is a restless, uneven structure with dense, drifting boundaries and vulnerable regions, silently reshaping itself, while technology passes through its thinnest places. The moon may have formed when another world struck Earth. Before the moon became the calm light in the night sky, it may have begun inside one of the most violent collisions in solar system history. The leading explanation for its origin proposes that more than 4 billion years ago, the young Earth was struck by a planetary embryo often called Theia, possibly comparable in size to Mars. This was not an asteroid impact leaving an ordinary crater. At the speeds involved, both worlds would have been intensely deformed, heated, and partly vaporized, throwing a vast amount of rocky material into orbit. Much of that debris may have formed a hot disk around Earth, where repeated collisions gradually gathered it into the early moon. The hypothesis helps explain several unusual features of the Earth-Moon system, including the moon's relatively small metallic core, the system's angular momentum, and the close chemical resemblance between many terrestrial and lunar rocks. That resemblance also creates one of the model's greatest puzzles. Early simulations often produced a moon made mostly from the impactor, yet samples returned from the moon can be remarkably similar to Earth's mantle. Researchers have proposed several possible solutions. The collision may have mixed material far more thoroughly than simple models predicted. Theia and Earth may have formed from similar material in the same region of the early solar system, or the impact may have occurred under a different angle, speed, or rotational state than the traditional scenario assumed. Recent isotope studies continue to support a high-energy origin, while showing that the precise sequence remains unresolved. The giant impact hypothesis is therefore not a completed eyewitness account, but the strongest framework built from lunar samples, orbital motion, laboratory measurements, and computer simulations. When you look at the moon, you may be seeing neither a captured stranger nor a simple piece gently separated from Earth, but the surviving result of two young worlds losing their original forms and creating something new from the wreckage. Its familiar light may be the final quiet expression of a collision so immense that it permanently changed the architecture of the sky. The young Earth may once have been covered by an ocean of magma. Long before Earth possessed blue oceans, stable continents, or a sky you could recognize, much of its surface may have glowed as a restless ocean of molten rock. The young planet was built through repeated collisions between smaller bodies, and each impact converted enormous amounts of motion into heat. Additional energy came from the sinking of heavy metals toward the center and the decay of short-lived radioactive elements present during Earth's formation. Together, these processes may have melted a large part of the rocky planet, creating one or more magma oceans that could have extended hundreds or even thousands of kilometers deep. This was not lava flowing between solid shores, but a world in which the shore itself had not yet formed. As Earth released heat into space, minerals began to crystallize from the melt, separating according to their density and chemistry. Some crystals sank, others remained suspended, and the mantle gradually developed a layered composition that may still influence the planet today. Gases dissolved in the magma also escaped as pressure changed, contributing water vapor, carbon compounds, nitrogen, and other ingredients to the early atmosphere. Only after the surface became cool enough could water remain as liquid rather than immediately returning to vapor. Scientists still debate how completely Earth melted, how long different molten layers survived, and whether a deep reservoir of magma persisted after the surface had hardened. The evidence must be reconstructed from mineral chemistry, laboratory experiments, meteorites, and computer models, because almost all rocks from this earliest period have been recycled or destroyed. Yet the broad lesson is clear. The solid world you know was not born solid. Its continents, atmosphere, and oceans emerged through cooling, separation, and chemical change within a planet that may once have shone from horizon to horizon. Beneath every quiet landscape lies the distant memory of that transformation, when Earth was not yet a home for life, but a glowing world, slowly learning how to become one. More than 99% of all species that ever lived are extinct. The living world surrounding you is not the complete story of life on Earth. It is the tiny surviving remainder. Paleontologists commonly estimate that more than 99% of all species that have ever existed are now extinct, although this number is not the result of counting every species individually. Such a census would be impossible because most organisms leave no recognizable fossil at all. Bodies are eaten, scattered, dissolved, or destroyed before burial, and even preserved remains can later be erased by erosion, heat, pressure, or the recycling of rock. Scientists instead reach the estimate by studying rates at which species appear and disappear, the typical geological duration of known groups, and the immense length of time during which life has been evolving. A species may flourish for hundreds of thousands or millions of years, and still occupy only a narrow interval in a history stretching back billions. Extinction also does not happen only during famous global catastrophes. Most species vanish through ordinary background extinction as environments shifted, competitors spread, food sources changed, diseases appeared, or populations became too small to recover. Nor does extinction mean that every organism suddenly failed. It means that a particular evolutionary lineage eventually reached its final individual and could no longer continue in that form. New species repeatedly arose while older ones disappeared, causing the composition of the biosphere to change like a language whose words are constantly being created and forgotten. The fossil record preserves only scattered moments from this process, favoring creatures with hard shells, bones, teeth, or bodies buried in suitable environments, while countless soft-bodied and microscopic forms may have vanished without leaving any trace we can recognize. Every species alive today is therefore both temporary and extraordinary, not the planned destination of evolution, but one branch that has remained unbroken until the present moment. When you see a bird, a tree, an insect, or even your own reflection, you're looking at survivors of an ancient process in which disappearance is normal and permanence is almost unknown. Life is abundant, but no particular form of life is guaranteed to remain. And perhaps that is what makes the living world around you more valuable than its familiarity allows you to notice. The worst mass extinction was not caused by an asteroid. The deadliest known collapse of life did not begin with a bright object crossing the sky, but with Earth opening vast wounds across what is now Siberia. About 252 million years ago, at the end of the Permian period, enormous volumes of magma rose through the crust during the formation of the Siberian Traps, a volcanic province whose remains cover a region of extraordinary size. The crisis was not simply one giant eruption that buried the planet in lava. Volcanic activity occurred in repeated phases, and some of the most damaging magma never reached the surface at all. It spread sideways through underground layers of coal, carbon-rich sediment, and other volatile-bearing rocks, heating them and helping release immense quantities of greenhouse gases and toxic compounds. As carbon dioxide accumulated, global temperatures rose sharply. Warm seawater could hold less oxygen, while changes in circulation made it harder to replace the oxygen being consumed in deeper regions. Large parts of the ocean became dangerously depleted, leaving marine animals trapped between increasing heat and shrinking supplies of breathable water. Additional stress may have come from ocean acidification, toxic metals, acid rain, damage to vegetation, and extreme climate variability. Recent research has even suggested that powerful and persistent El Niño-like conditions may have intensified drought, heat, forest loss, and ecosystem instability across the supercontinent Pangaea. The result was the most severe biological crisis known from the well-preserved fossil record, eliminating a vast majority of marine species and devastating life on land. Survival did not mean an immediate return to normal. Ecosystems remained unstable, and recovery required millions of years. Unlike an asteroid strike, which delivers much of its destruction in a sudden pulse, the end Permian catastrophe appears to have tightened around life through a chain of interacting changes, each making the next more difficult to escape. It reveals that a planet does not need an external enemy to become hostile. Sometimes the greatest danger comes from ordinary geological processes operating on an extraordinary scale, altering the atmosphere and oceans until the familiar conditions supporting life quietly cease to exist. A super eruption could cover entire regions in ash. The first sign of a super eruption might not be a wall of lava, but daylight slowly disappearing beneath a cloud of shattered rock. A super eruption is an exceptionally rare volcanic event capable of releasing more than 1,000 cubic kilometers of material, sending ash high into the atmosphere, where powerful winds can carry it far beyond the volcano itself. What falls from the sky would not be soft ash like the remains of a fireplace. Volcanic ash consists of tiny, sharp fragments of rock, minerals, and volcanic glass, often fine enough to enter engines, ventilation systems, water supplies, and human lungs. Close to the source, thick deposits could bury roads, damage buildings, destroy crops, and collapse roofs after accumulating or becoming heavy with rain. Farther away, even much thinner layers could close airports, contaminate machinery, reduce visibility, interrupt electricity, and make ordinary travel difficult across enormous areas. Computer simulations of a hypothetical Yellowstone supereruption show that heavy ash could cover much of the surrounding region, while smaller amounts might spread across large portions of North America. Although the exact pattern would depend on wind direction, eruption duration, particle size, and weather, the most serious consequences would not be identical everywhere, and ash thickness would generally decline with distance. Material injected high into the atmosphere could also temporarily reduce the sunlight reaching the surface and influence climate, but a super eruption would not automatically freeze the entire planet or erase humanity in a single moment. Such eruptions are extraordinarily uncommon, and the existence of a large volcanic system does not mean a super eruption is imminent, or even certain to happen again. The unsettling truth is more measured. One geological event could disrupt regions far beyond the place where the ground opened, turning air routes, farms, cities, and water networks into parts of the same distant disaster. You might think of a volcano as a danger belonging to one mountain, yet a super eruption reveals that the atmosphere can transform a local rupture into a continental problem, carrying pieces of the Earth across borders that nature has never recognized. Tsunamis can cross an ocean faster than a passenger jet. A tsunami racing beneath a ship may be moving faster than an airliner while leaving the people on deck completely unaware that it has passed. In the deep ocean, a tsunami can travel at more than 800 kilometers per hour, and in the deepest water, its speed may approach or exceed 970 kilometers per hour. This extraordinary motion is possible because a tsunami is not an ordinary surface wave pushed forward by wind. It is a disturbance involving almost the entire depth of the ocean, usually created when a large volume of water is suddenly displaced. The deeper the water, the faster that disturbance can propagate, allowing tsunami energy to cross an entire ocean in less than a day. Yet speed does not mean the open ocean wave must tower above the surface. Far from land, its height may be less than a meter, while the distance from one crest to the next stretches for tens or even hundreds of kilometers. A ship rises and falls too gradually to recognize it as a dangerous wave. The transformation begins as the tsunami reaches shallower coastal water. Friction with the seafloor and decreasing depth force the wave to slow. But the energy arriving from behind does not simply disappear. The waves become compressed, water piles upward, and currents grow more powerful. Depending on the shape of the seabed, harbor, bay, or coastline, the tsunami may arrive as rapidly rising water, a violent surge, or a sequence of floods rather than the single curling wall often shown in films. The first arrival may not be the largest, and dangerous currents can continue for hours after the sea initially moves inland or withdraws. This is why distant coastlines can be threatened by events that occurred thousands of kilometers away, and why warning systems use deep ocean sensors, seismic data, and coastal gauges to follow the disturbance before it arrives. The ocean can look calm while carrying enormous energy through its full depth, reminding you that danger is not always announced by what the surface allows you to see. Sometimes the fastest thing in the sea is almost invisible until the ocean floor rises beneath it and the coast gives that hidden motion a shape. Most of a continent called Zealandia lies beneath the Pacific Ocean. If the Pacific Ocean could be removed, New Zealand would no longer appear as an isolated pair of islands, but as the high ground of a vast sunken continent. Geologists call this region Zealandia, or Te Reo a Maui, a coherent area of continental crust covering roughly 4.9 million square kilometers, comparable in size to Greater India. About 94% of it lies below present sea level, leaving New Zealand, New Caledonia, and several smaller islands as its most visible peaks. Calling Zealandia a continent is not based simply on its size or on the fact that land once existed there. Researchers have identified several characteristics associated with continental masses. It stands higher than the surrounding deep ocean floor, contains a wide range of continental rocks, rather than mainly the basalt typical of oceanic crust, possesses crust that is thicker and less dense than ordinary seafloor, and has boundaries that distinguish it from nearby Australia. Rock samples recovered from islands, drill cores, and seabed expeditions reveal connected belts of granite, sedimentary rock, schist, and other materials that continue beneath the water, showing that these are not unrelated fragments scattered across the Pacific. Zealandia was once attached to the supercontinent Gondwana. During the later age of dinosaurs, its crust was stretched and thinned as Gondwana broke apart. Thinner continental crust floats lower on the underlying mantle, and over millions of years most of Zealandia subsided beneath the sea, rather than plunging downward during one sudden catastrophe. Parts of it have continued to deform, while geological forces raise sections of New Zealand above the water. There is no international authority that formally awards continent status, so terminology can vary. But the geological case published in 2017 persuaded many researchers that Zealandia is best understood as a continent rather than a collection of islands and submerged fragments. Its existence challenges the instinct to define continents only by their coastlines. The ocean can hide land from your eyes without changing the nature of the crust below. And Zealandia shows that even something nearly 5 million square kilometers in size can remain overlooked when water covers its outline. A map may seem to show where the continents end, but sometimes it shows only where the sea begins. Antarctica was once covered with forests. Beneath Antarctica's kilometers of ice lies evidence of a world that would seem impossible if you could see it today. Forests once grew across parts of the frozen continent, including regions close to the ancient South Pole. Fossil wood, leaves, pollen, spores, roots, and preserved soils reveal that Antarctica supported rich vegetation during several warmer periods, especially in the Cretaceous, when dinosaurs still walked the planet. A sediment core recovered from the seabed off West Antarctica contained an intact network of fossil roots from a temperate rainforest that existed roughly 90 million years ago at a latitude of about 82 degrees south. These plants endured months of winter darkness, yet the climate was mild enough for trees, ferns, and flowering vegetation to survive. This was possible because the atmosphere contained far more carbon dioxide than it does today. Global temperatures were much higher, and Antarctica lacked the immense reflective ice sheet that now cools the region. The forests were not tropical jungles filled with modern palms. Many resembled cool, wet woodlands containing ancient conifers and other plant groups adapted to unusual seasonal light. Growth rings preserved in fossil wood show that trees responded to long summers and dark winters, becoming dormant when sunlight vanished and growing rapidly when it returned. Antarctica was also connected more closely to other parts of the southern supercontinent Gondwana, allowing plants and animals to spread through landscapes that are now separated by ocean. The ice-covered wilderness you recognize is therefore only one chapter in a much longer history. A place can appear eternally frozen within the scale of a human life, while its rocks remember rain, flowing rivers, soil, and forests standing beneath a polar sky. Antarctica teaches you that climate does not merely change the appearance of a landscape. Given enough time, it can replace an entire living world with another so completely that only buried roots remain to prove the first one ever existed. The Sahara has repeatedly changed from desert to green savanna. The largest hot desert on Earth has not always been a desert, and the sand beneath it preserves the remains of vanished lakes, rivers, grasslands, and human settlements. During repeated African humid periods, stronger summer rains transformed large areas of the Sahara into a green landscape of savanna, wetlands, and freshwater basins. The most recent major green phase began roughly 11,000 years ago and faded several thousand years later, leaving behind ancient shorelines, lake sediments, pollen, animal bones, and rock art depicting swimmers, cattle, giraffes, and other creatures that could not live across most of the modern desert. The principal rhythm behind these transformations begins with slow changes in Earth's orbit and the direction of its tilted axis. Over thousands of years, these cycles alter how much summer sunlight reaches the northern hemisphere. When northern summers received stronger sunlight, the land heated more intensely, drawing moist air farther north and strengthening the West African monsoon. Rain encouraged vegetation to spread, and darker plant-covered ground absorbed more sunlight than pale desert sand. Reduced dust and growing lakes then influenced the atmosphere further, reinforcing the wet conditions. When the orbital pattern shifted again, monsoon rainfall weakened, plants retreated, dust increased, and the landscape returned toward aridity. These transitions were not perfectly regular or equally strong, because oceans, vegetation, ice, atmospheric gases, and regional geography all affected the result. The Sahara is therefore not a permanent geographical identity, but a climate state that has appeared, disappeared, and returned many times. Yet its ancient greening should not be treated as a simple prediction that the desert will soon become fertile again. Modern human-driven climate change is adding influences that do not follow the old natural rhythm alone. What now looks empty was once crossed by animals and people beside water, and what once seemed abundant eventually dried into silence. The desert invites you to question how easily the present disguises itself as permanence, because even a landscape vast enough to dominate a continent can be only a temporary expression of sunlight, wind, water, and time. Earth's atmosphere is frighteningly thin compared with the planet. Seen from orbit, the entire breathable world appears as a narrow blue line clinging to the curved edge of Earth. The atmosphere extends far above that visible band and gradually fades into space rather than ending at a solid boundary. But almost all of its useful mass is concentrated astonishingly close to the surface. About 80% of the atmosphere lies within the troposphere, whose average thickness is only around 12 kilometers. And this narrow region contains nearly all weather, clouds, and the air that supports everyday life. Even the commonly used boundary of space, about 100 kilometers above sea level, is tiny beside Earth's radius of more than 6,000 kilometers. Scaled down to the size of a basketball, the dense portion of the atmosphere would resemble little more than a tightly wrapped film around its surface. Air remains near the planet because gravity pulls gas molecules downward, causing pressure and density to be greatest close to the ground and to decrease rapidly with altitude. This is why climbing a high mountain can make breathing difficult, even though the summit is barely separated from sea level when compared with the size of the whole planet. The atmosphere may seem limitless when you stand beneath the sky, but its total mass is only about 1/1,000,000th of Earth's mass. It is not a deep ocean of air surrounding the planet, nor an indestructible dome that can absorb endless change without consequence. Human civilization, forests, agriculture, storms, and every breath you have ever taken exist at the bottom of an exceptionally shallow layer resting against a vast sphere of rock. The sky feels enormous because you experience it from within. Yet from outside, it looks fragile enough to vanish beneath the width of a fingertip. That change in perspective carries a quiet lesson. The environment separating a living world from space is not large because its importance is large. Nearly everything you call weather, climate, and breathable air is gathered within a planetary skin so thin that the wonder is not that it can be disturbed, but that such a delicate layer has protected and sustained life for so long. Earth's atmosphere is slowly leaking into space. Every second, a small part of the sky above you escapes Earth forever. At the outermost edge of the atmosphere, gas becomes so sparse that individual atoms can travel enormous distances without colliding with one another, and some acquire enough energy to overcome the planet's gravity. The lightest elements escape most easily. Hydrogen atoms can be heated by solar ultraviolet radiation until they drift away into space, while helium produced by radioactive processes within Earth also rises gradually and is lost. Other particles follow more complicated paths. Oxygen ions can be accelerated along electric fields. Energetic sunlight can break molecules apart, and interactions with charged particles from the sun can push atmospheric material outward. Spacecraft have directly observed some of these escaping particles, confirming that Earth's atmosphere is not a perfectly sealed container. Water is connected to this process because small quantities of water vapor reach high altitudes, where sunlight can separate it into hydrogen and oxygen. The hydrogen is light enough to escape more readily, making that loss effectively permanent. Yet there is no reason to fear that the air will suddenly drain away around you. The present escape rate is tiny compared with the atmosphere's immense supply, and gases are continually exchanged among the oceans, rocks, living organisms, and volcanic systems. Earth's gravity is also strong enough to retain heavier gases far more effectively than smaller worlds such as Mars. Over billions of years, however, atmospheric escape has helped shape the planet's chemistry, removing hydrogen and influencing how oxidized the surface became. It reminds you that even the air, which feels like the most constant and surrounding part of the world, is participating in a slow exchange with space. The atmosphere is not simply resting on Earth. It is being heated, broken apart, rebuilt, and quietly thinned one escaping atom at a time, while the planet continues to hold almost all of it close enough for you to take another breath. Earth may lose its oceans long before the sun becomes a red giant. The oceans may disappear while the sun still looks almost like the familiar star rising outside your window. The sun is gradually becoming brighter as conditions in its core change, and although this evolution is extremely slow, Earth will receive increasingly intense sunlight over the next 1 to 2 billion years. At first, the warmer climate would increase evaporation, placing more water vapor into the atmosphere. Water vapor itself traps heat, so this could strengthen the warming and eventually push Earth toward a moist greenhouse state, in which the upper atmosphere becomes far wetter than it is today. Once large amounts of water reach those heights, ultraviolet light can split the molecules apart. The heavier oxygen may react with surface materials or remain temporarily in the atmosphere, but much of the lighter hydrogen can escape into space. With each lost hydrogen atom, rebuilding the original water molecule becomes impossible, allowing the ocean inventory to decline over geological time. This would not resemble every sea boiling away on a single afternoon. Shorelines could retreat over immense periods. Rainfall patterns would fail. Remaining waters might become increasingly hot and saline, and isolated reservoirs could survive after the great open oceans had begun to disappear. Climate models do not agree on an exact date because clouds, atmospheric circulation, land distribution, carbon dioxide, and biological feedbacks can delay or accelerate the transition. Recent research suggests that surface habitability and some vegetation might persist for roughly 1.8 billion years under favorable assumptions, while other models place dangerous moist greenhouse conditions on somewhat different timescales. The central conclusion, however, remains: Earth does not need to wait for the Sun's red giant phase, expected several billion years from now, to lose the conditions that preserve its oceans. A star can end an ocean world without touching it, simply by growing brighter so gradually that no single generation could notice the change. The sea appears permanent because it is older than human memory. But on the lifetime of a star, even an ocean can become a temporary arrangement of molecules waiting to be lifted into the sky and separated forever. The Sun will, eventually, make Earth too hot for complex life. Earth's final biological crisis may begin not when the Sun engulfs the planet, but when ordinary sunlight becomes only slightly more intense than life can manage. As the Sun brightens, warmer temperatures will accelerate chemical weathering, the slow process by which rainwater and exposed rock help remove carbon dioxide from the atmosphere. This normally acts as a planetary thermostat. Greater warmth increases weathering, lower carbon dioxide weakens the greenhouse effect, and the climate is partly stabilized. In the distant future, however, that protection may become a trap. Continued carbon removal could leave too little carbon dioxide for many plants to perform photosynthesis efficiently, reducing the biological production that supports food webs and replenishes atmospheric oxygen. Forests and grasslands would not necessarily vanish at the same moment. Species with different photosynthetic strategies and tolerances would fail at different stages, and some hardy vegetation or microorganisms might endure far longer than large animals. At the same time, increasing heat would place direct stress on complex organisms, shrink habitable regions, disrupt reproduction, and make it harder for bodies to release excess warmth. A widely discussed 2021 model estimated that Earth's oxygen-rich atmosphere could persist for about another billion years before oxygen levels fall dramatically, most likely before severe ocean loss begins. Without abundant oxygen and widespread photosynthesis, animals with high energy demands would face conditions they could not simply evolve around. Newer work published in 2026 suggests that certain photosynthetic organisms could potentially survive closer to 1.8 billion years, showing that the exact lifespan of the biosphere remains uncertain and depends on plant physiology, climate feedbacks, and future atmospheric chemistry. What is far less uncertain is the direction of change. Long before the Sun becomes a swollen red giant, Earth will cease to support the rich and oxygen-hungry world you recognize. Life may continue in simpler refuges, hidden in water, soil, or cooler regions, but complex ecosystems will gradually lose the climate and chemistry that made them possible. The Sun that nourishes every leaf and powers nearly every food chain is therefore not an eternal guardian. Given enough time, the same light that allowed complex life to rise will become the pressure that asks it to leave, revealing how closely creation and ending can depend on the very same star. A hidden biosphere extends deep beneath Earth's surface. The living world does not end where roots disappear and sunlight can no longer reach. Far below forests, cities, deserts, and the ocean floor, microorganisms inhabit water-filled fractures, microscopic pores, buried sediments, and the spaces between mineral grains, forming what scientists call the deep biosphere. This is not a continuous underground jungle or a giant cavern filled with unfamiliar creatures. It is a scattered collection of dark, isolated habitats where life is often sparse, slow, and extraordinarily patient. Some communities occupy continental rock, while others live beneath the seabed in sediments that were deposited millions of years ago. A global comparison published in 2024 concluded that subsurface environments may contain more than half of all microbial cells on Earth, although estimates remain uncertain because only a tiny fraction of the underground realm has been sampled. These organisms include bacteria and archaea, with metabolisms unlike the surface life you know. Instead of depending directly on sunlight, many obtain energy from chemical reactions involving hydrogen, sulfur, methane, iron, or other compounds released through interactions between water and rock. Their activity can influence the movement of carbon, alter minerals, produce or consume gases, and quietly participate in planetary chemical cycles over immense spans of time. Life becomes less abundant as temperature rises and usable energy declines, so the deep biosphere has limits, but those limits are far below the familiar boundary of soil. Researchers must also distinguish genuine residents from contamination introduced during drilling, making every confirmed discovery the result of careful chemical, genetic, and geological testing. What has emerged is a different picture of Earth. The surface may display life most visibly, but it does not contain all of it. Beneath the landscapes you recognize lies a second biological realm, hidden not because it is small, but because stone has concealed it from human senses. It asks you to reconsider what a living planet really means, because Earth may be alive not only across its skin, but throughout a deep, fractured interior where entire communities pass their existence without ever knowing there is a sky. Some microbes survive kilometers below the ground. Nearly 3 kilometers beneath a South African gold mine, scientists discovered a form of life that survives without sunlight, fresh organic food, or oxygen from the surface. The organism, known as Candidatus desulphurudis audaxviata, was found in hot fracture water inside the Mponeng mine at a depth of about 2.8 kilometers. Genetic analysis showed that it overwhelmingly dominated the sampled community, creating one of the most striking examples of biological independence ever observed. Yet it does not live by feeding directly on radiation, as the discovery is sometimes inaccurately described. Radioactive elements naturally present in the surrounding rock release energy that can split water molecules, producing hydrogen. That hydrogen becomes a usable chemical fuel, while reactions involving nearby minerals provide sulfur compounds that the microbe can process. With these resources, it can obtain energy, build organic material from inorganic carbon, and acquire essential nutrients without relying on photosynthesis or material recently delivered from the surface. Its genome contains much of the machinery needed to maintain this isolated existence, including systems associated with repairing damage and surviving difficult conditions. The environment is dark, oxygen poor, pressurized, and heated to around 60 degrees Celsius. Yet to this organism, it is not extreme in the emotional sense humans give the word. It is simply home. Related members of the same lineage have since been detected in deep environments on other continents, suggesting that this survival strategy is not limited to one mine. Scientists remain cautious because drilling can connect previously separated waters and introduce contaminants, but repeated genetic and geochemical evidence confirms that genuine microbial ecosystems persist kilometers underground. Their existence changes the usual story of life's dependence on the sun. Sunlight powers most surface ecosystems, but it is not the only energy source biology can use. Somewhere below the world of leaves, weather, and seasons, a cell may spend its entire existence drawing power from reactions inside ancient rock, never rising, never seeing light, and never requiring the surface world to know that it is alive. Earth may have frozen, almost completely more than once. There were times when ice may have reached from the poles into the tropics, transforming Earth into something closer to a white planet than the blue world you know. The strongest candidates occurred during the Cryogenian period, especially the Sturtian glaciation beginning about 717 million years ago, and the later Marinoan glaciation, which ended around 635 million years ago. Geologists find glacial deposits on several continents in rocks that paleomagnetic evidence places near ancient tropical latitudes, suggesting that glaciers reached regions normally protected by intense sunlight. Some deposits contain dropstones, rocks carried by floating ice and released into marine sediment as the ice melted. Above many glacial layers lie unusual carbonate rocks known as cap carbonates, which appear to record dramatic environmental changes as the frozen conditions ended. Iron-rich formations also reappeared in some oceans during these intervals, possibly because prolonged ice cover altered how oxygen and dissolved iron moved through seawater. The process may have been strengthened by ice itself. As glaciers expanded, their bright surfaces reflected more sunlight, causing further cooling and allowing even more ice to form. Scientists still debate whether the oceans were sealed beneath continuous ice, covered by thinner or mobile ice, or interrupted by open water refuges. For that reason, Snowball Earth is a powerful hypothesis rather than a perfectly photographed reconstruction. Life clearly survived, perhaps in cracks within ice, beneath translucent ice near the surface, around areas of open water, or in environments supplied by chemical energy. The planet also appears to have entered this severe state more than once, meaning recovery from one global freeze did not guarantee permanent safety from another. Earth's history therefore contains climates far beyond anything human civilization has experienced, where familiar coastlines vanished and the distinction between continent and ocean was hidden beneath ice. The most unsettling lesson is not simply that Earth became cold, but that a living planet can move into conditions that seem almost incompatible with life and still carry its biological future quietly through the darkness, waiting for a world of ice to become a world of oceans again. Oxygen was once a poison that destroyed much of early life. The gas keeping you alive at this moment once entered Earth's environment as a dangerous chemical intruder. For much of the planet's early history, the atmosphere and oceans contained almost no free oxygen, and life consisted mainly of microorganisms adapted to oxygen-free conditions. Then, certain cyanobacteria developed oxygen-producing photosynthesis, using sunlight to extract energy from water and releasing oxygen as a byproduct. At first, this new gas did not accumulate freely. It reacted with dissolved iron, sulfur compounds, volcanic gases, and other materials that could absorb it, leaving geological evidence in oxidized minerals and ancient sediments. But roughly 2.4 billion years ago, oxygen began persisting in the atmosphere during the Great Oxidation Event. For many anaerobic organisms, this was not an improvement. Oxygen readily forms reactive molecules that can damage proteins, membranes, and genetic material, and microbes lacking protective enzymes would have been forced into oxygen-poor refuges or eliminated from newly oxygenated environments. Scientists cannot count how many lineages disappeared because these organisms were microscopic and left an incomplete fossil record, so claims of a precisely measured global mass extinction would go beyond the evidence. What can be said is that oxygen radically reorganized the biosphere, altered the chemistry of oceans and continents, and created strong evolutionary pressure for organisms capable of tolerating or using it. Some survivors developed antioxidant defenses, while others eventually exploited oxygen to release far more energy from food than most oxygen-free metabolisms could provide. That energetic advantage later helped make larger and more complex forms of life possible, while atmospheric oxygen also contributed to the formation of an ozone shield that reduced harmful ultraviolet radiation. The substance you experience as a symbol of freshness and survival was therefore neither naturally benevolent nor universally welcome. It was a waste product that transformed the planet, closing countless biological paths while opening others that would eventually lead to animals, forests, and you. Life did not receive oxygen as a gift. It was confronted by a poison adapted to its presence, and slowly turned the threat into one of the foundations of the modern world. Faults can remain, locked for centuries before moving in seconds. A silent fault can spend centuries preparing for a movement that will be completed before you fully understand what is happening. Two blocks of crust may be pushed steadily past one another by regional geological forces, yet rough surfaces, bends, and strong patches along the fault can prevent them from sliding smoothly. The fault is then described as locked, but locked does not mean inactive. Rock on both sides continues to deform extremely slowly as strain accumulates, much like a rigid object being bent farther while its weakest connection refuses to release. Modern satellite measurements can detect this process by showing how the ground changes position by only a few millimeters each year, even where the fault itself appears motionless. Eventually, the stress on part of the locked zone may exceed the friction holding it in place. Rupture begins in a relatively small area and can spread rapidly along the fault, allowing rock that has been distorted for generations to shift within seconds. The resulting displacement sends seismic waves outward and leaves the surrounding crust in a new arrangement, though it rarely releases every bit of stored strain. Scientists search for evidence of earlier ruptures by digging trenches across faults, where buried scarps, broken sediment layers, and displaced soils can reveal earthquakes that occurred before written records. Radiocarbon dating can place approximate ages on these events and show that some faults have waited hundreds or even thousands of years between major ruptures. Yet these intervals are not dependable countdown clocks. One section may rupture earlier than its average history suggests. Another may remain quiet much longer, and earthquakes on neighboring faults can alter the surrounding stress. This is why a long period without an earthquake does not prove that a fault is safe, but it also does not allow scientists to name the exact day when it will fail. The quiet years are not empty years. They are part of the earthquake cycle, recorded in deformation too gradual for your senses to notice. Human attention is naturally drawn to the moment the ground moves, but the deeper story has been unfolding throughout the lifetimes before it. While streets were built, families grew older, and the fault beneath them continued to hold a strain no one could feel. A powerful earthquake can make the entire planet ring. After the strongest earthquakes, the shaking does not truly end when buildings become still and the surface appears calm again. A sufficiently powerful rupture sends seismic waves through the interior and around the surface of Earth, and some of those waves repeatedly interfere with one another until the entire planet begins vibrating at its natural frequencies. Seismologists call these patterns normal modes, or free oscillations, though they are often described more simply as Earth ringing like a bell. The comparison is useful, but the sound would not resemble a bell you could hear. Most of the vibrations occur at frequencies far below human hearing. Their movements are extremely small by the time they spread around the globe, and precise instruments are required to detect them. Some modes make Earth alternately expand and contract in a slow-breathing motion. Others distort its shape, causing different regions to rise and fall in coordinated patterns, while twisting modes move parts of the planet sideways without significantly changing its volume. The magnitude 9.5 earthquake in Chile in 1960 provided some of the earliest clear global observations of these oscillations, and the magnitude 9.1 Sumatra-Andaman earthquake in 2004 strongly excited them again. Certain modes remained measurable for weeks, and the lowest frequency vibrations can persist longer because they lose energy very slowly. These signals are more than an impressive after effect. Their exact frequencies and decay rates depend on Earth's density, elasticity, internal boundaries, rotation, and three-dimensional structure. By comparing measured oscillations with predicted ones, scientists can study regions that no drill or camera could ever reach, and can also estimate properties of the earthquake that set the planet vibrating. Each mode is a response from the whole Earth to a sudden release of energy in one limited place. A fault may rupture beneath one ocean or continent, yet the resulting motion travels through the globe, circles it repeatedly, and brings distant instruments into the same event. Long after human ears declare the disaster finished, the planet continues carrying its memory as motion, rising and falling by amounts too small to feel, but large enough to reveal that Earth is not an immovable platform. It is a resonant body, and under sufficient force, every layer can become part of the vibration. A megathrust earthquake can move an entire coastline. A coastline that has remained familiar for generations can be lifted, lowered, and shifted toward the sea during a single earthquake. This happens during the largest megathrust earthquakes, which occur where one great slab of Earth descends beneath another along an enormous, gently sloping fault. When hundreds of kilometers of that boundary rupture together, the land above it does not move as one rigid piece. Some areas rise as the crust bends upward, while others sink as the stored deformation is suddenly rearranged. During the magnitude 9.2 Great Alaska Earthquake of 1964, vertical changes affected an area roughly 2/3 the size of California. Parts of the coast subsided by as much as about 2.5 meters, while sections of Montague Island rose by more than 11 meters. Harbors were left at different heights relative to the tides. Forests sank into salt water, and shorelines no longer occupied the positions shown on existing maps. The 2011 earthquake off northeastern Japan produced another dramatic example. Tens of meters of movement occurred along parts of the offshore fault, and sections of the Japanese coast dropped by more than 0.5 meter, increasing their exposure to the tsunami that followed. These changes are called seismic deformation because they occur during the earthquake itself, but their consequences can persist for decades or centuries. A lowered coast floods more easily during storms and high tides, while uplifted reefs, beaches, and former seabeds may be stranded above the water. Scientists measure the displacement with satellite positioning, radar images, tide gauges, coastal surveys, and biological clues such as drowned trees or marine organisms suddenly raised beyond the reach of waves. Not every megathrust earthquake produces identical movement, because the pattern depends on the shape, depth, and amount of slip across the fault. Yet the possibility changes how you think about a coastline. It is not simply the place where permanent land meets a restless ocean. During a sufficiently powerful rupture, the land itself can join the motion, and in only a few minutes, the boundary between a country and the sea can be rewritten. Some volcanoes remain hidden beneath Antarctic ice. Antarctica may conceal volcanic mountains that have never been seen directly, buried beneath ice thick enough to erase their shapes from the surface. West Antarctica lies above a broad region of stretched and fractured crust known as the West Antarctic Rift System, where volcanic activity has occurred over millions of years. Because much of the bedrock is hidden beneath the ice sheet, researchers cannot identify its volcanoes by simply looking for cones, craters, or lava fields. Instead, aircraft carry ice-penetrating radar that sends signals through the ice and records the landscape below, while magnetic, gravity, and seismic measurements reveal structures and heat sources that may have volcanic origins. Surveys have identified numerous cone-like formations beneath West Antarctica, and researchers have suggested that the total number of known or suspected volcanic edifices there may reach about 138. That figure does not mean 138 volcanoes are currently erupting. Many could be dormant or extinct, and a mountain's shape alone cannot always prove its volcanic origin. Evidence for more recent activity comes from other clues, including volcanic ash preserved within ice cores, unusual heat beneath glaciers, earthquake patterns, and chemical traces. A study of the West Antarctic ice sheet found evidence consistent with an active volcanic heat source beneath part of the continent, while another identified volcanic material showing that at least one subglacial eruption was capable of sending debris into overlying ice. Heat rising from buried volcanic systems can melt ice locally at its base, add water beneath a glacier, and influence how easily the ice slides over bedrock. But this does not mean a hidden eruption would instantly melt Antarctica or trigger a sudden global collapse. The effect would depend on the volcano's location, size, eruption style, and connection to the surrounding ice and water systems. What makes these volcanoes so compelling is not an approaching catastrophe, but how completely ice can hide an active geological landscape. Above them stretches one of the coldest surfaces on Earth. Below them may lie fractured rock, rising heat, old lava, and mountains whose existence must be inferred from echoes. Antarctica appears silent because its ice covers the evidence, yet silence at the surface does not guarantee stillness underneath. Most of Earth's volcanic activity happens beneath the ocean. While people watch a small number of famous volcanoes on land, most of the planet's eruptions occur where almost no human being can witness them. Scientific estimates commonly place roughly 3/4, and possibly as much as 80%, of Earth's volcanic activity beneath the ocean. Much of it is concentrated along the global mid-ocean ridge system, an underwater volcanic chain stretching for nearly 65,000 kilometers through every major ocean basin. Eruptions there often happen thousands of meters below the surface, under pressure so great that volcanic gases cannot expand as violently as they often do in shallow water or open air. Molten rock emerges through cracks, meets near freezing seawater, and cools rapidly, sometimes forming rounded masses called pillow lava. An eruption capable of transforming the seafloor may therefore produce no towering ash cloud, glowing horizon, or distant sound that a person on land would recognize. The ocean absorbs the heat, hides the light, and muffles much of the event. Researchers find these eruptions using seafloor maps, underwater microphones, remotely operated vehicles, changes in water chemistry, and instruments placed on submarine volcanoes. Some are discovered only after scientists return to a previously mapped area and find new lava covering the old terrain. At Axial Seamount in the Northeast Pacific, repeated eruptions have been documented using networks of pressure sensors and seismic instruments, allowing researchers to observe how an underwater volcano inflates before releasing magma. Even with such technology, only a small fraction of submarine volcanic systems is continuously monitored, so eruptions can begin and end without ever entering human records. This hidden activity changes the image of Earth as a planet whose volcanoes are mainly isolated mountains rising above inhabited land. The continents show only the visible minority. Beneath the waves lies a far larger volcanic realm, operating across distances that circle the globe and continuing whether or not anyone is present to name each eruption. The ocean's surface may look unbroken and calm, but far below it, fire is reaching the water in places no sunlight has ever touched. Another supercontinent may form, hundreds of millions of years from now. The world map. You know, may be only the opening frame of a collision that will not finish for another 200 million years. Continents are still moving, oceans are still widening or shrinking, and if plate tectonics continues, most of Earth's major landmasses may eventually gather into another supercontinent. Scientists have proposed several possible futures, but none should be mistaken for a certain prediction. In one scenario called Amasia, the Americas and Asia move toward one another as the Arctic Ocean closes, creating a vast northern landmass. Another model, Novopangia, assumes that the Pacific continues shrinking while the Atlantic keeps expanding, eventually bringing the Americas into collision with Eastern Asia. Pangaea Ultima, sometimes called Pangaea Proxima, instead imagines the Atlantic reversing its present growth and closing, reuniting the Americas with Africa and Europe. A fourth possibility, Orica, would require both the Atlantic and Pacific to close while new oceans develop elsewhere. These dramatically different maps exist because scientists can measure how plates move today, but cannot know exactly where new subduction zones will form, or how mantle circulation will reorganize over hundreds of millions of years. A small change in one ocean basin could redirect the motion of an entire continent long before the final assembly. Whichever arrangement emerges, the interior of the new supercontinent could become extremely dry, because moisture from surrounding oceans would struggle to reach its center, while vast mountain systems might rise where continental blocks collide. Coastlines familiar to future life would appear in places now occupied by deep water, and many modern nations would lie folded into mountain belts or separated from the sea. The important truth is therefore not that one particular future map has already been decided, but that the present map has not. Earth is still arranging its surface, and the continents beneath today's borders are traveling toward a meeting no human civilization will survive long enough to witness. Continents are temporary shapes that will eventually disappear. Look carefully at the outline of any continent, because geology has no obligation to preserve it. Africa, Europe, Asia, Australia, Antarctica, and the Americas appear permanent only because their transformation is far slower than a human life. A continent is not a single unbreakable slab, but a complicated assembly of ancient crustal fragments, old collision zones, sedimentary basins, volcanic regions, and younger material joined over immense periods. Heat rising beneath a landmass can stretch its crust until deep rifts open, as is happening today in East Africa. If the separation continues long enough, seawater may enter, new oceanic crust may form between the divided regions, and parts of the continent that once shared one landscape can drift into different hemispheres. Elsewhere, an ocean can narrow until two continents collide, compressing their edges, stacking slices of crust, and raising mountain chains from rocks that once rested beneath the sea. Wind, rivers, glaciers, and landslides then wear those mountains down, carrying their remains into basins where they become new rock. Continental crust is generally too buoyant to sink easily into the mantle in the same way as dense oceanic crust, so parts of ancient continents can survive for billions of years. But survival of the material does not preserve the shape. Coastlines migrate, fragments break away, islands are welded onto larger landmasses, and former margins become buried hundreds of kilometers inland. The rocks beneath one modern country may once have belonged to several different continents assembled at different times. Far in the future, the Atlantic coastlines, Mediterranean boundaries, and familiar curves printed on maps will all be erased. Not necessarily because their rocks vanish, but because those rocks will be rearranged into forms that no longer resemble the world you recognize. A continent is therefore less like a permanent object and more like a temporary pattern made from durable pieces. You may live as though geography is the stage on which history occurs, yet over deeper time, geography is also one of the characters, continually breaking itself apart and returning in another form. Pangaea was not Earth's first supercontinent. Pangaea feels ancient until you realize that it was merely the latest giant assembled from the ruins of even older worlds. It came together mainly between about 320 and 250 million years ago, but geological evidence points to earlier supercontinents that existed long before animals walked on land. Rodinia formed roughly 1 billion years ago, bringing together many of the continental cores that would later become parts of North America, Africa, Antarctica, Australia, and Asia. Before Rodinia, another supercontinent generally called Nuna or Columbia assembled around 1.8 billion years ago, although scientists continue debating the exact positions of several of its pieces. Still older groupings, including Canorland and collections known as supercratons, have also been proposed, but the further researchers travel into deep time, the more uncertain the reconstruction becomes. The evidence is not preserved as an ancient global map. Geologists must rebuild these lost arrangements by measuring magnetic signals locked inside rocks, which can reveal the latitude at which those rocks formed. They compare mountain belts that now end at ocean margins, search different continents for rock layers of the same age and chemistry, match episodes of metamorphism and volcanism, and study zircon crystals whose internal records can survive the destruction of the original landscape. When several independent clues connect distant regions, fragments now separated by oceans can be placed beside one another in a former world. Even then, longitude is often difficult to determine, and later heating or deformation may partially erase the original magnetic record. For this reason, ancient supercontinent maps are scientific reconstructions with varying levels of confidence, not photographs of a settled past. What they show is that Pangaea's breakup was not the beginning of continental motion. It was one moment in a far older history of gathering and separation that had already transformed Earth repeatedly. The ground carrying you may contain pieces of mountains raised during collisions that happened before complex animals existed, before familiar oceans opened, and before Pangaea had even begun to assemble. The oldest journeys of the continents are not written on their surfaces. but hidden inside rocks that remember belonging to worlds with names humanity invented only after those worlds were gone. Almost none of the original ocean floor still exists. The oldest chapters of Earth's oceans have been torn from the planet's geological record. Although liquid water may have covered parts of Earth for more than 4 billion years, almost none of the seafloor from those early oceans remains in its original location. The oceanic crust beneath today's seas is surprisingly young. Its average age is only about 55 million years, and nearly all of it is younger than roughly 200 million years. That makes even the most ancient intact seafloor younger than the earliest dinosaurs and far younger than many rocks preserved within continents. The reason is hidden in the character of oceanic crust itself. It is relatively thin, dense, and rich in basalt. So as it cools and ages, it sinks lower and becomes increasingly capable of descending into Earth's interior. Over immense periods, entire ocean basins have closed, carrying their floors downward until heat and pressure altered the rock beyond recognition. This destruction has erased evidence that might have revealed the precise locations of vanished oceans, the movements of the earliest plates, and the environments in which ancient life first developed. Geologists sometimes recover fragments called ophiolites, pieces of old oceanic crust and upper mantle that were pushed onto continents rather than carried into the depths. These rare survivors can preserve basalt, deep-sea sediments, and rocks once formed beneath ancient ocean ridges, but they are incomplete scraps rather than untouched sections of the original seafloor. Scientists must therefore reconstruct most early ocean history from indirect clues preserved in continental rocks, mineral grains, chemical signatures, and mountain belts formed when old oceans disappeared. You can walk across landscapes containing rocks more than 3 billion years old, yet travel to the bottom of the deepest modern ocean and find a floor that is geologically young. The continents have kept fragments of memory, while the oceans have repeatedly erased their own foundations. Beneath the water lies not an ancient surface patiently preserved since Earth's beginning, but a temporary floor whose oldest pages have already descended beyond recovery. The ocean floor is constantly being created and destroyed. Across the darkness of the deep sea, the planet is laying down new ground while removing old ground elsewhere. New ocean floor forms along the global network of mid-ocean ridges, where tectonic plates gradually separate and hot mantle material rises beneath the opening. As pressure decreases, part of this material melts, producing magma that cools into basalt and becomes fresh oceanic crust. Some of it erupts onto the seabed, while more solidifies within the crust below, building a layered foundation rather than a single sheet of frozen lava. The newborn seafloor begins hot, elevated, fractured, and almost free of sediment. As it travels away from the ridge, it cools, contracts, becomes denser, and slowly sinks to greater depths. Sediment settles onto it grain by grain. Hydrothermal fluids alter its minerals, and underwater volcanoes may add new structures to its surface. Magnetic minerals within the cooling basalt also align with the direction of Earth's magnetic field at that time, creating matching bands on opposite sides of spreading ridges. These symmetrical patterns became some of the clearest evidence that the seabed is moving outward rather than remaining fixed. Creation, however, cannot continue forever without removal. At deep ocean trenches, an aging oceanic plate may bend beneath another plate and descend into the mantle. Water and altered minerals carry downward influence, melting and volcanic activity above, while sediments may be scraped away, folded against a continent, or pulled into the depths with the plate. Not every section of seabed follows the same path, and some thick plateaus or fragments resist complete descent, but the global pattern is unmistakable. Oceanic crust is manufactured, transported, transformed, and consumed. The total surface of Earth does not simply grow because new seabed is forming. Creation in one region is broadly balanced by destruction in another. The floor beneath the ocean is therefore less like the permanent bottom of a container, and more like material moving through a planetary system. Every basin has an age, every ridge is a birthplace, and every trench marks a region where part of the visible world begins its journey out of sight. Churning ocean of liquid metal creates Earth's magnetic field. No permanent magnet is hidden at Earth's center. The planet creates its magnetic field through motion. Surrounding the solid inner core is an outer core, more than 2,000 kilometers thick, composed mainly of electrically conductive liquid iron mixed with nickel and lighter elements. This metallic fluid is constantly moving as Earth releases internal heat. Hotter, more buoyant material rises, cooler material sinks, and the gradual solidification of the inner core releases both heat and lighter chemical elements into the surrounding liquid. These differences provide energy for convection, but rising and sinking alone would not produce the organized planetary field measured at the surface. Earth's rotation bends and arranges the flowing metal into large, twisting patterns. Because the fluid conducts electricity, its motion moves electrical charge, and moving charge generates magnetism. That magnetic field then influences the flowing metal, helping create further electrical currents and sustain the process. This self-maintaining system is known as the geodynamo. It is not a simple circular current and does not behave like a machine with neatly visible parts. Core motion is turbulent, affected by heat escaping unevenly into the mantle above, and shaped by forces that operate under pressures and temperatures impossible to reproduce fully in a laboratory. Scientists investigate it using satellite observations, records preserved in magnetic rocks, seismic evidence, computer simulations, and experiments with rapidly rotating fluids. These studies show that the field observed around Earth is the distant surface expression of complex motion occurring thousands of kilometers below. If the liquid metal stopped moving in the necessary way, the global field would gradually fade rather than remain permanently fixed inside the planet. The magnetism surrounding you is therefore not merely something Earth possesses, it is something Earth is continually producing. Far beneath the calm surface, an electrically conducting ocean is turning heat, rotation, and chemical separation into an invisible structure extending far into space. What appears from above as a silent magnetic presence is, deep below, the consequence of a planet still cooling, separating, and moving within itself. The center of Earth is solid, even at thousands of degrees. At the deepest point on the planet, iron remains solid in a place hot enough to melt it easily at the surface. Earth's inner core is a sphere roughly 1,220 kilometers in radius, composed mainly of iron with nickel and smaller amounts of lighter elements, yet no sample of it has ever been brought into a laboratory. Its solid state was discovered by listening to earthquakes. In 1936, Danish seismologist Inger Lehmann studied pressure waves that appeared inside a region where the accepted model of a completely liquid core suggested they should barely be detected. She proposed that some waves were being bent or reflected by a separate central body, revealing a solid inner core surrounded by liquid metal. Modern instruments have since recorded waves that pass through, reflect from, and reverberate across this hidden boundary, allowing researchers to refine the picture. The explanation for its solidity lies in the fact that a material's melting temperature is not fixed under every condition. Near Earth's center, pressure is millions of times greater than atmospheric pressure, forcing atoms into an extremely dense arrangement and raising the temperature required for the iron alloy to melt. Earth's internal temperature falls below this elevated melting threshold at the center, so the metal crystallizes even though it remains intensely hot. Scientists test this idea by squeezing microscopic pieces of iron between diamonds, heating them with lasers, and using computer calculations to estimate how iron behaves under conditions that cannot be maintained on a human scale. The inner core is not necessarily a flawless, motionless crystal. Seismic waves travel through it at different speeds depending on their direction, suggesting that many iron crystals may be aligned, deformed, or organized into complex regions. Its outermost layers may even flow very slowly while remaining solid, much as other solids can deform when pressure acts for long enough. The center of Earth therefore challenges the simple division between hot and melted, or solid and unchanging. Matter obeys the conditions surrounding it, and in the most compressed place on the planet, heat that would create a liquid ocean elsewhere is held inside a solid sphere that humanity discovered without ever seeing it. The inner core is slowly growing as the planet freezes from within. Earth is quietly growing an enormous crystal at its center. The liquid outer core has been cooling throughout the planet's history, and where it meets the inner core, part of its iron-rich mixture gradually crosses the boundary between liquid and solid. New crystals attach themselves to the surface of the inner core, increasing its size by an amount far too small to observe directly over a human lifetime, but significant across geological time. This process is sometimes described as Earth freezing from within. Although the word freezing does not mean the core is becoming cold. The temperature remains thousands of degrees, but the melting point rises with depth, allowing metal to solidify as the planet slowly loses heat. The crystallization does more than enlarge the central sphere. When iron becomes solid, it does not accept all the lighter elements mixed into the surrounding liquid equally. Some of those elements are expelled back into the outer core, producing buoyant material that rises through the denser liquid. At the same time, crystallization releases latent heat, the energy given off when a liquid changes into a solid. These thermal and chemical effects help stir the outer core and contribute to the convection needed to sustain Earth's magnetic field. The inner core is therefore not merely an inactive object sitting at the center. Its growth influences the behavior of the much larger liquid region around it. Researchers are still debating when this crystallization began. The inner core is almost certainly younger than Earth itself, and several modern estimates place its origin around 1 billion years ago, while other evidence suggests it may be only several hundred million years old. The uncertainty exists because scientists must combine laboratory measurements of iron, models of heat escaping through the mantle, magnetic records preserved in ancient rocks, and seismic observations of the inner core's present structure. Growth may also be uneven. Differences in heat loss around the core mantle boundary could make iron crystallize faster in some regions than in others, while slow deformation inside the inner core may redistribute the solid material afterward. Far below every landscape, Earth is continuing a phase change that began long after the planet formed and will continue as long as sufficient heat escapes. The center is becoming larger not through the addition of new matter, but through a gradual rearrangement of matter already present, turning a portion of the hidden liquid into solid history, one layer at a time. The mantle is solid rock that still flows like an extremely slow liquid. A piece of mantle rock held in your hand would feel completely solid, yet a mantle made from the same kind of rock can slowly change shape across millions of years. This apparent contradiction comes from the difference between how matter behaves over seconds and how it behaves under continuous heat and pressure for geological ages. Earth's mantle extends from beneath the thin crust to a depth of about 2,900 kilometers and is composed mainly of solid silicate minerals. Seismic shear waves travel through most of it, providing strong evidence that it is not a global underground ocean of magma. Small amounts of melt exist in certain regions, especially where temperature, pressure, water content, or chemistry allows rock to begin melting. But the mantle as a whole remains solid. Its movement occurs through a process called creep. At the microscopic level, imperfections within mineral crystals shift, atoms slowly migrate, and grains change shape or slide past one another. A force too weak to break the rock immediately can therefore deform it if that force continues for thousands or millions of years. Temperature matters greatly. Hotter rock deforms more easily, while cooler rock near the surface behaves more rigidly and can fracture instead. Water stored in minerals, grain size, composition, and stress also affect how resistant the mantle is to flow, which is why its viscosity varies from place to place and with depth. One of the clearest demonstrations comes from regions once buried beneath enormous ice sheets. The ice pressed the crust downward and displaced mantle material beneath it. After the ice melted, the land began rising as mantle rock slowly moved back toward its earlier arrangement, and that uplift is still measurable today in parts of northern Europe and North America. Laboratory experiments compress and heat mantle minerals to investigate their deformation, while satellite measurements, gravity data, and observations of post-glacial rebound reveal how the real planet responds over longer periods. Calling the mantle a liquid is therefore misleading, but calling it motionless is equally wrong. On the scale of an earthquake, it behaves as an elastic solid through which vibrations can travel. On the scale of a mountain range or an ice age, it behaves as a material capable of continuous flow. The difference is not hidden magic within the rock, but time. A human life is brief enough to experience stone as the symbol of permanence. Earth's life is long enough to watch that same stone bend, circulate, and reshape the world above it. The magnetic field can weaken without the planet becoming defenseless. A weaker magnetic field would not leave Earth suddenly naked beneath the sun. The field surrounding the planet is often imagined as a rigid shield that is either fully active or completely absent. But its real behavior is far more complicated. Its strength varies across the surface, changes over time, and can become uneven without disappearing everywhere at once. Geological records show that during major magnetic transitions, the average field at the surface may fall dramatically, in some cases to a small fraction of its usual strength, while weaker and more complex magnetic regions continue to exist around the planet. Charged particles from the Sun would then be able to approach Earth more easily in certain areas, increasing radiation exposure for satellites, spacecraft, and people traveling at very high altitudes. Auroras could appear farther from the poles. Satellite electronics might experience more disruptions, and intense solar storms could become a greater challenge for communication, navigation, and electrical systems. Yet this would not mean that deadly solar radiation immediately reaches every living thing on the ground. The atmosphere remains a powerful physical barrier, absorbing and scattering much of the dangerous radiation that arrives from space, while the remaining magnetic field would continue redirecting many charged particles. Earth has passed through long periods of weak and disordered magnetism before, and researchers have found no reliable connection between magnetic reversals and mass extinctions. That does not make weakening meaningless. A technological civilization extending into orbit is far more vulnerable to space weather than ancient organisms were. The consequences would be serious, mainly because modern life depends on machines operating above much of the atmosphere, or through long electrical networks sensitive to rapid magnetic changes. The field should therefore be understood not as a single wall, but as a changing system of protection shared with the atmosphere. It can bend, develop weak regions, and lose strength without surrendering the planet entirely. What feels reassuring is not that Earth possesses an indestructible shield, but that its defense has layers, and even when one layer becomes less reliable, the living world below is not immediately abandoned to space. Earthquakes are the only reason we know what the planet looks like inside. Every large earthquake briefly turns the entire planet into a medical scan. The title sounds absolute, and science requires one careful correction. Earthquakes are not literally the only source of information about Earth's interior, because gravity, magnetism, heat flow, laboratory experiments, and the chemistry of rocks also provide important clues. But seismic waves generated by earthquakes are the main reason scientists can map the planet's hidden layers with such detail. When a fault ruptures, it releases several kinds of waves. Pressure waves compress and expand material in the direction they travel, allowing them to move through both solids and liquids. Shear waves move material sideways, and because a liquid cannot support that kind of shearing motion, these waves disappear when they encounter a sufficiently large liquid region. As waves descend, their speed changes according to the density, temperature, composition, and physical state of the material around them. Their paths bend, reflect from boundaries, or arrive at distant stations later than expected. Some parts of the globe receive no direct waves of a particular type. creating shadow zones whose shapes reveal major internal boundaries. Seismologists compare the arrival times of waves from thousands of earthquakes recorded by instruments around the world, then use those differences to construct three-dimensional images called seismic tomography. The result resembles a planetary scan. Faster regions may indicate colder, denser material, while slower regions may reveal hotter rock, unusual chemistry, or small amounts of melt. The images are not photographs, and they do not show sharp colors hidden inside Earth exactly as diagrams suggest. They are interpretations built from how waves behaved along many crossing paths, so resolution is best where earthquakes and recording stations provide dense coverage and weaker where data are scarce. Artificial explosions can generate useful seismic waves for studying shallower structures, but they cannot match the energy of major earthquakes traveling through the entire globe. Each powerful rupture is therefore both a disaster at the surface and an involuntary experiment for deep Earth science. The planet cannot be opened, illuminated, or visited at most depths, yet it reveals its structure by changing the speed and direction of vibrations passing through it. We know what lies below not because Earth allows us to see inward, but because every layer leaves a different signature on motion, and earthquakes provide the force that makes those hidden signatures audible. Diamonds can carry material from hundreds of kilometers below. Some diamonds are not merely gemstones, they are sealed containers that have carried pieces of inaccessible Earth to the surface. Most diamonds form deep within the thick roots of old continents, but a rare group known as super-deep diamonds is believed to originate much farther below, in the mantle transition zone and, in some cases, possibly the lower mantle. As a diamond crystal grows, it can trap microscopic grains of nearby minerals, droplets of fluid, or small pockets of material within its structure. Jewelers may regard these inclusions as imperfections, yet geologists value them because they can preserve evidence of the pressure, temperature, chemistry, and reactions present when the diamond formed. The diamond acts like a strong protective chamber, surrounding the inclusion and helping it survive a journey through regions where its original mineral form might otherwise change. One remarkable diamond from Brazil contained ringwoodite, a high-pressure mineral associated with depths between roughly 410 and 660 kilometers. Ringwoodite had long been created in laboratories and predicted to exist inside Earth, but finding it enclosed in a natural diamond provided direct physical evidence that this mineral really forms within the mantle. Its chemistry also showed that the surrounding region held water within mineral structures, although one tiny inclusion cannot prove that the entire layer contains the same amount. Other diamonds carry combinations of minerals and chemical signatures interpreted as evidence. That material from the ocean floor or continental surface was dragged downward before becoming involved in diamond formation. Much later, rapidly rising magma transported the diamonds toward the surface in unusual volcanic eruptions, bringing their microscopic passengers with them. The diamond itself may have remained underground for hundreds of millions or even billions of years before that final ascent. Scientists study these inclusions with X-rays, lasers, microscopes, and spectroscopy, sometimes without removing them from their host, because releasing the pressure can cause delicate minerals to expand, crack, or transform. Each inclusion offers only a minute and local sample, so researchers must resist treating one diamond as a complete description of the deep mantle. Yet these fragments remain among the closest things humanity possesses to material delivered naturally from depths no machine could reach. A diamond may appear clear and empty when held to the light, but its most important feature can be the dark speck trapped inside it. A piece of an unseen world carried upward by a crystal strong enough to keep one moment of deep earth from being erased. Some water beneath your feet has never seen the surface. A drop of water can be older than the mountain above it and remain hidden so completely that no rainstorm, river, or ocean has touched it for more than 1 billion years. Deep inside ancient continental rock, Water occupies narrow fractures and microscopic spaces that may be almost entirely disconnected from the modern water cycle. Unlike groundwater in a shallow aquifer, which can be replenished by rain over years or centuries, these deep fluids move through rock so slowly that they can remain isolated for spans of time longer than the history of complex animal life. In mines in the Canadian Shield, researchers have sampled highly salty water flowing from fractures more than 2 kilometers below the surface. By examining noble gases dissolved within it, including forms of helium, neon, argon, and xenon produced or trapped over immense periods, they concluded that parts of the fluid system had residence times of at least 1 billion years and possibly much longer. Similar ancient water has been discovered deep beneath South Africa, showing that such isolation is not unique to one location. Calling this water ancient does not necessarily mean that every molecule has remained perfectly still since its formation. Fluids can mix, chemical reactions can produce new water or alter old water, and small exchanges may occur along fractures. What the evidence reveals is that the deep system as a whole has been separated from surface circulation for extraordinary lengths of time. The surrounding rock continually changes the trapped fluid, making it far saltier than seawater and filling it with hydrogen and other chemical products. Some hydrogen is generated when natural radiation from uranium and other elements splits water molecules, while additional reactions between water and minerals can create energy-rich compounds. These processes occur without sunlight and without material recently carried down from above. Scientists date and study the fluids not because they could provide a practical reservoir of drinking water, but because they preserve information about ancient crustal chemistry and the long-term stability of hidden environments. The water coming from a deep fracture may have been sealed away before familiar continents, plants, or animals existed, continuing its chemical life while the surface was transformed again and again. You usually imagine water as the most restless substance on Earth, forever rising into clouds and returning as rain, yet some of it has escaped that familiar rhythm. Beneath your feet are fluids that have spent geological ages inside darkness, reminding you that not every part of Earth participates in the world you can see. Carbon is constantly being dragged deep into the planet. Every day, part of the carbon that once moved through air, seawater, shells, and living cells begins a descent into Earth that may last millions of years. Carbon dioxide dissolves in the ocean. Marine organisms use carbon to build tissue and calcium carbonate shells, and the remains of these processes settle onto the seafloor as organic material and carbonate-rich sediment. Chemical reactions also lock carbon into altered oceanic crust. When an oceanic plate reaches a subduction zone and bends beneath another plate, it carries this carbon-bearing material downward, like a geological conveyor disappearing into the planet. The journey does not have one simple ending. As pressure and temperature increase, minerals break down and release water-rich fluids capable of dissolving and transporting carbon. Some of that carbon rises into the mantle above the descending plate, contributes to magma formation, and eventually returns to the atmosphere through volcanic gases. Another portion may be scraped from the plate before it descends deeply, while some remains locked in stable minerals such as carbonate or graphite and continues much farther into the mantle. Under suitable conditions, deeply transported carbon can become part of diamonds, carbon-rich melts, methane-bearing fluids, or long-lived mantle reservoirs isolated from the surface for millions or billions of years. Scientists still debate the exact fraction that returns rapidly and the fraction that survives the descent because the answer differs among subduction zones. A young, warm plate may release carbon differently from an old, cold one, and the amount carried downward depends on the sediments, crustal chemistry, water content, and temperature of the system. Researchers investigate these pathways through volcanic gases, high-pressure experiments, chemical signatures in rocks, and microscopic inclusions preserved in minerals. This hidden transfer is known as part of the deep carbon cycle, and it has helped regulate Earth's atmosphere over geological time. If every piece of carbon entering a trench returned immediately through nearby volcanoes, the long-term balance of atmospheric carbon dioxide could be very different. If too much remained trapped indefinitely, the surface could gradually lose an essential ingredient for climate and life. Earth's habitability has therefore depended partly on an exchange that no organism can watch. Carbon descending inside rock and later returning in altered form. The carbon within your body may once have crossed an ocean, entered stone, traveled into Earth, and emerged again through fire before becoming available to life. What appears to be a surface element is participating in a cycle deep, enough to connect breathing organisms with the slow movement of the planet itself. The largest, earthquakes, can change the length of the day. Single earthquake can move enough of the planet's mass to alter how quickly the entire Earth rotates. The change is unimaginably small, measured in millionths of a second, but it follows the same physical principle you see when a spinning skater draws their arms closer and turns faster. Earth's rate of rotation depends not only on how much mass it contains, but on how that mass is distributed relative to its rotational axis. During an exceptionally large earthquake, vast sections of crust shift vertically and horizontally across a fault hundreds of kilometers long. This rearranges a tiny part of the planet's mass and slightly changes its moment of inertia. The resistance a rotating object has to changes in its spin. If enough mass moves closer to the axis, Earth rotates a little faster and the day becomes shorter. Movement in another pattern could instead slow the rotation and lengthen the day. After the magnitude 9.0 Tohoku earthquake struck Japan in 2011, calculations by NASA scientist Richard Gross suggested that the redistribution of mass may have shortened the day by about 1.8 microseconds. The same modeling indicated that Earth's figure axis, the axis around which its mass is balanced, shifted by roughly 17 centimeters. This is not the same as changing the orientation of the planet's astronomical rotation axis in space, and it did not produce a noticeable change in clocks, seasons, or daily life. The estimated effect was also too small to isolate easily from the many other influences continually changing Earth's rotation. Winds, ocean currents, atmospheric pressure, groundwater movement, tides, melting ice, and interactions between the mantle and core all move mass and cause the length of day to vary. Atomic clocks and astronomical observations can measure these broader variations with extraordinary accuracy. But determining the contribution of one earthquake usually requires a physical model of the rupture and the resulting displacement. The significance is therefore not that humanity lost a measurable portion of its day, but that an event concentrated along one fault can affect a property belonging to the entire planet. The earthquake does not push Earth like an external hand. It reorganizes Earth from within, causing the rotating body to adjust to its new distribution of weight. The day feels like a fixed unit imposed by the heavens, yet its duration is partly shaped by air, water, ice, and moving rock. Even time as measured by the turning planet is not perfectly separate from geology. And when enough of Earth shifts in a few violent minutes, the rotation carrying every person through day and night responds. Mount Everest is not the point farthest from Earth's center. The mountain reaching farthest from the center of Earth is not the one carrying the title of highest above sea level. Mount Everest rises about 8,149 meters above mean sea level, making it the highest summit by the measurement used on ordinary maps. Yet Ecuador's Mount Chimborazo extends farther outward from the planet's center. Chimborazo is only about 6,263 meters above sea level, but it stands almost directly on the equator, where Earth's surface lies farther from the center than it does at the latitude of Everest. This difference is large enough that Chimborazo's summit is more than 2 kilometers farther from Earth's center than Everest's peak. The apparent contradiction comes from the fact that a mountain can be measured in several legitimate ways. Everest wins when height is measured above mean sea level. Hawaii's Mauna Kea becomes taller when measured from its submarine base to its summit. Chimborazo wins when the measurement begins at the center of the planet. Mean sea level itself is not a simple, perfectly even shell, because the ocean is influenced by Earth's gravity, rotation, currents, temperature, and the uneven distribution of mass within the planet. Surveyors therefore use carefully constructed reference surfaces to determine elevation rather than measuring every mountain from one visibly level ocean. Chimborazo's unusual record does not make it more difficult to climb than Everest, place it above more of the atmosphere, or change which summit has the greatest elevation above sea level. It simply reveals that the answer to what is the highest point on Earth depends on where you decide height begins. You may expect nature to provide one unquestionable champion, but measurement always carries a point of view. Everest is highest above the sea. Mauna Kea rises the greatest distance from its deep base, and Chimborazo reaches farthest from the planetary center. The mountains have not changed, only the question has, and perhaps that is the deeper lesson hidden in their heights. Even facts that seem simple can open into several truths when you examine the invisible reference line beneath them. Gravity is not equally strong everywhere on Earth. Your weight would change slightly if you carried the same scale from the equator to the poles, climbed a mountain, or stood above unusually dense rock. Gravity is often introduced as though it has one uniform strength across Earth, but the pull you experience varies from place to place for several different reasons. Distance is one of them. The farther you move from the planet's center, the weaker the gravitational attraction becomes. So gravity is slightly lower at high elevations than it is near sea level. Latitude matters as well. Earth's rotation carries locations near the equator around a wider circle each day, producing a small outward effect that reduces the downward force measured by a scale. Near the poles, that rotational effect is weaker, so effective gravity is generally stronger. Beneath these broad patterns are smaller variations caused by the uneven distribution of mass. Dense rock formations can increase the local gravitational pull, while sedimentary basins, underground cavities, or regions containing less dense material can produce slight reductions. Mountains add mass, but their height also moves you farther from the center, so their gravitational influence cannot be understood from appearance alone. Scientists measure these differences with highly sensitive instruments called gravimeters and with satellites that detect subtle changes in Earth's gravity field. These measurements can help reveal buried geological structures, track changes in groundwater, monitor the loss of ice, and show how mass moves through oceans and the atmosphere. Gravity maps therefore contain information about parts of the planet that cannot be seen directly. The variations are far too small to make you float in one country or feel crushed in another, and an ordinary bathroom scale may not clearly reveal them. Yet precise clocks, surveying systems, satellites, and scientific experiments must account for these differences. Gravity is not a perfectly smooth command issued equally from every point below you. It is the combined result of the planet's mass, motion, shape, altitude, and hidden interior. You feel only a steady downward pull, but within that familiar sensation lies a detailed map of where Earth is dense, where it is light, where it rises, and where it has quietly rearranged itself. Earth is not a perfect sphere. From far enough away, Earth looks almost perfectly round, but precise measurement reveals a planet with a wider waist, flattened poles, irregular terrain, and a surface that refuses to fit one simple shape. Because Earth rotates, material near the equator is carried around the rotational axis, and the planet bulges slightly outward there. Its equatorial radius is about 6,378 kilometers, while its polar radius is close to 6,357 kilometers, creating a difference of roughly 21 kilometers. Geometrically, this makes Earth closer to an oblate spheroid than a true sphere, although even that is only an approximation. Continents, trenches, mountain ranges, ice sheets, and variations in the distribution of rock create smaller irregularities. For navigation and mapping, scientists use a smooth mathematical form called a reference ellipsoid, which provides a practical surface on which positions can be calculated. For elevations and the behavior of water, they also use the geoid, an irregular gravity-based surface that approximates global mean sea level. The geoid is sometimes displayed as a wildly lumpy model, but those visualizations greatly exaggerate its variations so they can be seen. In reality, Earth remains extraordinarily round when judged against its enormous size. Its highest mountains and deepest trenches are small surface imperfections compared with the planet's full diameter, more like tiny variations on a vast curved body than dramatic distortions. Earth's form is also not absolutely frozen. Moving ocean water, atmospheric circulation, earthquakes, changes in groundwater, melting ice, and the slow adjustment of land formerly pressed down by glaciers redistribute mass and can produce minute changes detectable by modern instruments. This means that even the best model of Earth's shape is a carefully measured representation of a moving planet, rather than a permanent geometric object. The globe on a desk is useful because it simplifies what cannot be reproduced at that scale. But the real Earth has no perfectly smooth outline and no flawless mathematical surface. You live on something nearly spherical, yet subtly flattened, locally uneven, and continually adjusting. A world round enough to resemble a simple idea from space, but complex enough to resist that idea whenever you measure it closely. The deepest ocean trench could almost swallow Mount Everest. Lower Mount Everest into the deepest known part of the ocean, and its summit would still remain more than 2 kilometers beneath the waves. Challenger Deep, located within the Mariana Trench in the western Pacific, reaches close to 11 kilometers below sea level, while Everest rises about 8.8 kilometers above it. The comparison is dramatic, but the trench is not a narrow crack shaped like an open mouth waiting to consume a mountain. It is a vast, sloping depression formed where the Pacific Plate bends and descends beneath the smaller Mariana Plate. As the oceanic plate is forced downward, the seafloor curves into one of the deepest boundaries on Earth, creating a region known as the Hadal Zone. Water pressure at the bottom exceeds 1,000 times the pressure you experience at sea level, enough to destroy an ordinary submarine almost instantly by crushing every unprotected cavity. Even specialized exploration vehicles must use thick pressure-resistant spheres, carefully designed seals, and materials able to survive forces that try to collapse them from every direction. Yet the trench is not empty. Microorganisms live within its sediments, and animals such as amphipods and sea cucumbers survive in nearby depths through flexible bodies, pressure-adapted proteins, and chemical systems that continue functioning where ordinary cells would fail. The exact maximum depth is difficult to determine because different expeditions follow slightly different paths, use instruments with different uncertainties, and must correct for temperature, salinity, and the speed of sound through seawater. Measurements therefore vary by several meters rather than producing one perfectly final number. What does not change is the scale. Human beings often treat mountains as the greatest vertical structures on the planet because they rise into the part of the world we can see, name, and climb. But Earth's most extreme descent lies hidden beneath a calm ocean surface, where the distance downward is greater than the height of any summit above it. Everest appears to reach toward the edge of the atmosphere, yet the Mariana Trench reveals that the planet contains a deeper direction, one capable of placing the highest mountain entirely inside darkness before its peak could ever touch the light. Most of the seafloor has never been seen directly by human eyes. There are landscapes covering most of Earth that no person has ever looked at, even through the window of a submersible or the camera of a remotely operated vehicle. The seafloor occupies more than 2/3 of the planet's surface, but direct visual exploration has reached only a very small fraction of it. Scientists can still map broad underwater features without seeing them. Ships send pulses of sound toward the bottom and measure how long the echoes take to return, allowing multi-beam sonar systems to build detailed images of ridges, trenches, plains, canyons, and volcanic mountains. Satellites add another layer of information by measuring tiny changes in the height of the ocean surface caused by variations in gravity. a massive underwater mountain pulls slightly more water toward it, producing a subtle bulge at the surface that can reveal the structure below. These techniques have transformed our understanding of the oceans. But a map created from sound or gravity is not the same as a photograph. It may show the shape of a canyon while revealing nothing about the animals living on its walls, the color of its sediments, the remains of a ship resting inside it, or the small geological structures hidden between widely spaced measurements. Direct observation requires cameras, crewed submersibles, autonomous vehicles, or remotely operated machines, all of which must survive darkness, corrosion, cold, enormous pressure, and the difficulty of communicating through water. An expedition can spend hours descending, observe a narrow strip of bottom, and return with footage covering an area that would be almost invisible on a global map. Even places described as explored may have been crossed only once, along a single route, while enormous nearby regions remain unseen. New species, volcanic vents, geological faults, wrecks, and entire ecosystems can therefore exist in areas that have technically been mapped but never visually inspected. You live on a planet whose continents have been photographed from aircraft and satellites in extraordinary detail. Yet beneath the ocean, knowledge still arrives as scattered beams, brief camera lights, and incomplete paths through darkness. The unknown seafloor is not confined to one distant corner. It forms most of the ground on Earth. The familiar world is the smaller part, while the larger landscape remains below, present in our maps, but still waiting to be witnessed. Deadly brine pools form lakes beneath the ocean. At certain places on the seafloor, a submarine can approach what appears to be the shoreline of a lake, even though it is already surrounded by ocean water. These strange formations are brine pools, bodies of water so salty and dense that they sink into depressions and remain partly separated from the seawater above them. Their boundaries can look remarkably sharp, producing ripples and waves when a vehicle disturbs the surface, as though one liquid world has been placed inside another. Many brine pools form where ancient salt deposits buried beneath the seabed dissolve into surrounding water. The resulting brine may be several times saltier than normal seawater, making it heavy enough to collect rather than mix quickly into the ocean. In places such as the Gulf of Mexico, the Red Sea, and parts of the Mediterranean, these pools can range from small patches to large basins with recognizable shores. Their beauty hides an environment lethal to many animals. The water may contain little or no oxygen, while high concentrations of hydrogen sulfide, methane, and dissolved salts can disrupt cells, damage tissues, and overwhelm organisms that enter without special adaptations. Fish or crabs that remain inside too long can become stunned or die, and their bodies may be preserved along the bottom because decay proceeds differently in the oxygen-starved brine. Yet the pools are not biologically empty. Microorganisms capable of using sulfur, methane, and other chemicals thrive where sunlight contributes nothing. Around some pool margins, mussels, tube worms, and other animals live in partnership with bacteria that produce food through chemosynthesis. This creates a remarkable boundary. The center may function as a toxic trap for ordinary marine life, while the edge supports dense communities built from the same chemicals that make the water dangerous. Researchers study these places to understand extreme ecosystems, ancient ocean chemistry, and the kinds of environments that might exist beneath the icy surfaces of distant moons. A brine pool reminds you that even water can form a border within water, and that the difference between a habitat and a grave can be only a few meters. To human eyes, it resembles a quiet lake resting beneath the sea. To the creatures approaching its shore, it is an invisible change in chemistry powerful enough to decide which forms of life may cross and which must remain outside. Hydrothermal vents support life without sunlight. When scientists first descended to hydrothermal vents in 1977, they expected a barren volcanic landscape and instead found crowded communities thriving in darkness. These vents form where seawater enters cracks in the oceanic crust, travels downward, and is heated by hot rock or nearby magma. During that journey, the water reacts chemically with the crust, loses much of its oxygen, and collects dissolved metals, hydrogen sulfide, hydrogen, methane, and other compounds. It can then surge back into the ocean at temperatures exceeding 300 degrees Celsius without immediately boiling because of the immense surrounding pressure. When the hot fluid meets cold seawater, dissolved minerals solidify into particles, building chimneys that may release dark clouds known as black smokers. The vents themselves provide heat and chemicals, but the true foundation of these ecosystems is microscopic life. Certain bacteria and archaea perform chemosynthesis, extracting energy from reactions involving substances such as hydrogen sulfide, and using that energy to build organic matter from carbon dioxide. Larger animals then eat these microbes or form intimate partnerships with them. Giant tube worms offer one of the strangest examples. Adults have no mouth, stomach, or digestive tract. Instead, they contain an organ filled with bacteria that manufacture nutrients for them, while the worms supply those bacteria with the chemicals required for the reaction. Mussels, clams, shrimp, crabs, and many other animals gather around different vents, but individual vent fields can be short-lived. Mineral deposits may block the flow, geological activity may shift, and an oasis crowded with life can become inactive, forcing species to disperse or die. It is also important not to exaggerate their independence. Chemosynthesis does not require sunlight, yet many vent organisms use oxygen dissolved in seawater, and much of that oxygen was originally produced by photosynthetic life near the surface. Vent ecosystems therefore reveal an alternative beginning for a food web, not necessarily complete separation from the rest of the planet. Still, their discovery overturned the old assumption that every rich ecosystem must begin with sunlight. In a world without dawn, plants, or seasons, life found another doorway into energy, showing that darkness is not always the absence of opportunity. Sometimes it simply demands a chemistry that surface life never needed to learn. Life survives in trenches, where sunlight has never reached. At the bottom of an ocean trench, the weight of the water is so great that ordinary biological machinery should begin to fail, yet animals still move through the sediment. The Hadal zone begins at depths of about 6 kilometers and continues into the deepest trenches. Where sunlight has never penetrated, temperatures remain close to freezing, and pressure can exceed 1,000 times that at the surface. Pressure is dangerous not because it simply flattens every creature, but because it can distort proteins, interfere with chemical reactions, and force cell membranes into a more rigid state. Hadal organisms survive through adaptations operating at the molecular level. Their membranes often contain fats that remain flexible under compression, while small protective compounds known as piezolites help proteins keep their proper shape. One such compound, trimethylamine oxide, is found in increasing concentrations in many deep-living fish and is associated with the faint marine smell of their tissues. These animals also avoid gas-filled structures that would be difficult to maintain under such pressure. Hadal snailfish have soft bodies, reduced bones, and gelatinous tissues, making them appear delicate, even though their biology is tuned to conditions that would destroy most surface organisms. Amphipods, sea cucumbers, worms, and diverse microbes live deeper still, occupying sediments and trench walls that were once assumed to be nearly lifeless. Trenches are not uniform pits. They're steep slopes, isolated basins, earthquakes, currents, and falling carcasses can concentrate nutrients in some places, producing patches of surprising abundance beside areas of extreme scarcity. Different trenches may also function like separate islands, allowing populations to evolve in isolation and creating species found nowhere else. There may be a physiological depth limit for fish because the concentration of pressure-protecting compounds required at greater depths would eventually disrupt the balance of water inside their cells. But invertebrates and microbes continue below the deepest known fish habitats. Much remains uncertain because sampling these regions is extraordinarily difficult. machines must descend for hours, operate under crushing force, and examine only a minute part of an enormous trench. Yet every expedition weakens the idea that life belongs only to comfortable environments. The deepest animals do not survive by defeating pressure. They survive because every part of their bodies has been shaped around it. What would be an instant disaster to you has become the ordinary condition of their existence, suggesting that habitability is never defined by one species looking outward from the environment it happens to call normal. Marine snow is constantly falling through the deep ocean. Far below the waves, the ocean is filled with a snowfall made from the remains of life. Marine snow begins in the sunlit upper layers, where plankton grow, animals feed, and countless particles are produced by ordinary biological activity. Dead microorganisms, fragments of plants and animals, fecal pellets, mucus, discarded feeding structures, dust, and tiny mineral grains collide and stick together, forming loose flakes that drift downward. Some are barely visible, while others grow into soft clumps several centimeters across. Bacteria colonize them during the descent, decomposing the organic matter and changing its chemistry as it falls. Small animals may eat the flakes, break them apart, or package the material into faster sinking pellets. So marine snow is not simply waste passing through empty water. It is a moving habitat and a constantly recycled food supply. The journey to the seabed can take weeks, and most of the original material never completes it. Much is consumed or converted back into carbon dioxide and nutrients in the upper and middle ocean. Only a fraction reaches great depths, but that fraction is crucial because it delivers energy into regions where photosynthesis cannot occur. Marine snow also forms part of the biological carbon pump. Phytoplankton near the surface take carbon dioxide from seawater while growing, and when some of that carbon sinks inside particles, it can remain isolated from the atmosphere for decades, centuries, or longer. The efficiency of this transfer depends on temperature, plankton communities, particle size, bacterial activity, currents, and how rapidly the flakes descend. Large fecal pellets or mucus-rich aggregates can sink quickly, while small particles may hover, dissolve, or be eaten long before reaching the bottom. Researchers collect sinking material in sediment traps and observe it with cameras, but measuring the global flow remains difficult because the snowfall changes with season and location. To you, the deep ocean may seem cut off from the living brightness above, yet it receives a continuous record of surface activity. Every bloom of plankton, every feeding event, and every microscopic death can contribute to a slow rain through kilometers of water. The ocean's greatest migration is therefore not made only by swimming animals. It is also the quiet downward movement of matter, carrying yesterday's surface life into darkness and binding the fate of the atmosphere to a snowfall almost no human eye will ever see. Pressure in the deep ocean can crush unprotected machines. A deep-sea vehicle does not have to be struck by anything to be destroyed. The surrounding water itself can collapse it in a fraction of a second. Ocean pressure increases steadily with depth because every object below the surface must support the weight of the water above it, and this force presses inward from every direction rather than only from the top. At several kilometers down, each small section of a machine's exterior may be carrying a load equivalent to hundreds of atmospheres. Solid metal does not simply flatten under these conditions, but any weak seam, poorly designed window, damaged cable opening, or air-filled chamber can become the starting point of failure. If the wall of a pressure vessel bends inward even slightly, its shape may lose the ability to distribute the load evenly, allowing the surrounding water to crush it almost instantaneously in an implosion. The collapse happens so quickly because water rushes into the failing space, while the trapped air is violently compressed, releasing heat and shock waves inside the structure. Engineers protect crude submersibles by placing people inside compact spherical or cylindrical pressure holes made from materials such as titanium or specially strengthened steel. curved shapes are valuable because they spread external pressure more evenly than broad, flat panels. Robotic vehicles often use a different strategy. Instead of keeping every component inside one large air-filled body, engineers place electronics in small pressure housings, fill some systems with non-conductive oil that can transmit pressure safely, and use syntactic foam containing countless tiny hollow spheres to provide buoyancy without large, vulnerable air spaces. Every housing is modeled, machined with extreme precision, inspected for microscopic flaws, and tested under pressure before entering the sea. Even then, repeated dives can fatigue materials and seals, so survival depends on continuous maintenance rather than one successful design. Deep-sea animals avoid the same problem because most of their bodies contain water and have few large gas-filled cavities, allowing internal and external pressure to remain more closely balanced. A machine built for the surface carries pockets of ordinary atmospheric conditions into a world where those conditions cannot naturally exist. The ocean does not crush it out of violence. It simply occupies the space the machine can no longer defend. Deep exploration is therefore not merely a journey through distance, but an attempt to preserve a tiny artificial room against a force that grows stronger with every meter of descent. Much of the oxygen you breathe comes from ocean life. The source of your next breath may be an organism so small that thousands of them could drift through a drop of seawater without ever being noticed. Scientists estimate that roughly half of Earth's current oxygen production comes from the ocean, primarily through photosynthesis performed by phytoplankton, algae and cyanobacteria living in sunlit surface waters. Like plants on land, these organisms absorb carbon dioxide and water, use sunlight to build organic material, and release oxygen during the process. Their individual contribution is microscopic, but the ocean covers most of the planet, and immense populations can multiply rapidly when light and nutrients are favorable. Blooms stretching across hundreds of kilometers may become visible from satellites as swirls of green or turquoise, yet much of the work is performed by cells invisible to your eyes. One cyanobacterium called Prochlorococcus is among the smallest known photosynthetic organisms and may account for as much as 1/5 of oxygen production across the biosphere, despite being far smaller than any tree leaf. There is, however, an important distinction between producing oxygen and permanently adding oxygen to the atmosphere. Marine organisms also breathe, bacteria decompose dead material, and chemical reactions consume much of the oxygen created in the ocean. The oxygen atoms entering your lungs today cannot usually be labeled as coming from one recent plankton bloom, because the atmosphere contains a vast reservoir mixed over long periods. For oxygen to accumulate on geological timescales, some organic carbon must escape immediate decomposition, often by sinking and becoming buried in sediments. Otherwise, the oxygen released during photosynthesis is largely consumed when that organic matter is broken down. This means the familiar claim that every second breath comes directly from the ocean is a useful illustration of the ocean's enormous productivity, but not a literal alternation between marine and terrestrial oxygen molecules. The deeper truth is more interesting. Forests are not the only living systems maintaining the chemistry around you. Across the illuminated skin of the sea, countless drifting cells are continually rebuilding part of the atmosphere, while also feeding marine food webs and moving carbon through the planet. You breathe without seeing them, depending partly on organisms with no roots, no branches, and no awareness that the air above the waves will eventually enter a human body far from the coast. The ocean stores far more heat than the atmosphere. The greatest reservoir of heat in the climate system is not the air warming around you, but the enormous body of water beneath the horizon. Water can absorb a large amount of energy while changing temperature relatively slowly, and the ocean contains vastly more mass than the atmosphere. Because of this combination, only the upper few meters of the global ocean can store roughly as much heat as the entire atmosphere above it. Across its full depth, the difference becomes overwhelming. Measurements show that the ocean has absorbed more than 90% of the excess heat accumulating in Earth's climate system from human-driven greenhouse gas emissions. This does not mean every part of the sea warms evenly. Sunlight heats the surface directly, winds stir the upper layers, currents transport warm water across ocean basins, and turbulence slowly carries some energy downward. Certain regions absorb heat more efficiently, while others release it back into the atmosphere, influencing rainfall, drought, storms, and seasonal temperatures far from the coast. Scientists measure ocean heat using ships, satellites, moored instruments, and thousands of autonomous Argo floats that repeatedly descend and rise while recording temperature and salinity. Ocean heat content is often more revealing than surface temperature alone, because a small warming spread through an immense volume of water can represent an extraordinary amount of stored energy. That energy has consequences even when you cannot feel it directly. Warmer seawater expands, contributing to sea level rise. Marine heat waves can persist long enough to damage coral reefs and reorganize ecosystems. Additional heat can intensify the rainfall and wind potential of some tropical cyclones when other atmospheric conditions are favorable. It can also return to the air later, meaning the ocean delays part of atmospheric warming while committing the planet to changes that unfold slowly. This buffering effect has protected the surface from experiencing the full immediate impact of the energy imbalance, but the heat has not vanished. It has been transferred into a place capable of hiding it beneath waves. The ocean is therefore not merely responding to climate change. It is storing its history. Each layer of warming water carries energy absorbed during earlier years, and long after a hot day has passed from human memory, part of its larger planetary cores can remain below, moving through currents that will influence seasons and coastlines still to come. A global conveyor belt moves water around the planet. The water beside one coastline may eventually travel through distant oceans, descend into darkness, and return to the surface centuries after the people who first watched it have disappeared. This slow planetary circulation is often called the global ocean conveyor belt. Although it is not a single current following one neat track, it is a connected system shaped by winds, Earth's rotation, the arrangement of continents, and differences in seawater density. Near the surface, winds drive broad currents that carry warm water away from the tropics and cooler water toward lower latitudes. In high-latitude regions, especially the North Atlantic and around Antarctica, seawater loses heat to the cold atmosphere. When sea ice forms, much of its salt remains in the surrounding water, making that water saltier, heavier, and more likely to sink. Dense water can descend thousands of meters and spread through the deep ocean, flowing beneath warmer layers that are moving in other directions. It does not remain on the bottom forever. Turbulent mixing, winds over the Southern Ocean, and upwelling in several ocean basins gradually return deep water toward the surface, where it can rejoin faster surface circulation. A complete journey can take hundreds or even thousands of years, and an individual parcel of water may mix with countless others before completing anything resembling a circuit. The conveyor metaphor is therefore useful but simplified. The real ocean behaves more like a network of branching roads, merging pathways, and slow vertical exchanges. This motion carries more than water. It transports dissolved oxygen into the deep sea, brings nutrients back toward illuminated surface waters, redistributes salt, and moves carbon between the atmosphere and the ocean interior. Without such circulation, deep waters would become chemically different, marine productivity would shift, and heat would be distributed around the planet in another pattern. The sea may appear divided into named oceans, yet water does not recognize those borders. Beneath the waves, the Atlantic, Pacific, Indian, Southern, and Arctic oceans participate in one connected movement, linking places separated by continents and generations. The ocean's deepest currents are too slow for you to watch, but they reveal a planet in which even water that appears still is already partway through a journey around the world. Changes in ocean circulation could reshape regional climates. region can experience a different climate even while the entire planet continues warming, simply because the ocean changes where it delivers heat and moisture. One of the most closely studied systems is the Atlantic Meridional Overturning Circulation, or AMOC, which carries warm, salty upper ocean water northward through the Atlantic and returns colder deep water toward the south. As the northward flowing water releases heat, it influences temperatures around the North Atlantic and contributes to weather patterns affecting Europe, Eastern North America, parts of Africa, and regions far beyond the ocean itself. If this circulation weakens, the consequences would not be limited to one band of water. Heat could accumulate farther south, rainfall belts could shift, marine ecosystems could be reorganized, and sea level could rise more rapidly along parts of the North American Atlantic coast, because a weaker current changes the slope of the ocean surface. Changes in North Atlantic temperature can also influence storm tracks, seasonal rainfall, and the location of tropical rain belts, meaning that some regions could become wetter while others face greater drought risk. Increasing greenhouse gases warm the ocean, and additional freshwater from rainfall and melting ice can reduce the density of northern surface water, making it more difficult for that water to sink and participate in overturning circulation. Climate assessments conclude that the AMOC is very likely to weaken during this century, but the size and timing of that weakening remain uncertain. Scientists also do not expect the cinematic scenario in which the circulation suddenly stops and freezes entire continents within days. A complete collapse would produce severe and widespread effects, but whether and when such a threshold could be crossed is still an active research question, and direct observations cover only a small part of the circulation's natural variability. The important lesson is more subtle than a disaster film. Regional climates depend not only on how much heat Earth contains, but on where the ocean carries that heat. The same global warming trend can produce different local outcomes because currents redistribute energy rather than creating it equally everywhere. A coast may grow warmer, cooler relative to surrounding regions, wetter, drier, or more exposed to rising seas as distant water changes its route. Climate is therefore not painted onto the planet one color at a time. It is woven from moving air and water, and when one of the ocean's great patterns changes, places thousands of kilometers apart can feel the threads being pulled. An asteroid impact ended the age of non-avian dinosaurs. The age of dinosaurs ended when a mountain-sized object arrived from space faster than any creature on Earth could perceive or escape. About 66 million years ago, an asteroid roughly 10 kilometers wide struck near what is now Mexico's Yucatan Peninsula, creating the buried Chicxulub crater, which spans around 180 kilometers. The immediate destruction around the impact region was almost unimaginable, but the event became globally lethal because of what entered the atmosphere afterward. Vast quantities of pulverized rock, vaporized material, sulfur-rich aerosols, dust, and soot were thrown high above the surface. Some debris returned through the atmosphere at extreme speed, contributing to intense heating and fires in many regions, while fine particles and aerosols remained aloft and reduced the sunlight reaching the ground. Temperatures fell, photosynthesis declined sharply, and food chains began collapsing from their foundations. Plants and plankton could no longer produce energy normally. Herbivores lost their food, and predators soon lost theirs. Acid rain, darkness, cooling, and changes in ocean chemistry added further pressure to ecosystems already damaged by the initial blast. The extinction eliminated about 3/4 of Earth's species, including every known non-avian dinosaur. Yet dinosaurs did not vanish completely. Birds are living dinosaurs descended from small feathered ancestors that survived the crisis, possibly because some could eat seeds, insects, or other resources that remained available after fresh vegetation became scarce. Survival also favored certain animals able to burrow, shelter in water, reproduce quickly, or live on flexible diets. The connection between the impact and extinction is supported by several independent clues. A worldwide sediment layer enriched in iridium, an element uncommon in Earth's crust, but more abundant in asteroids. Shocked minerals and impact debris found across distant regions, the enormous crater dated to the extinction boundary, and a sudden transformation in fossils above and below that layer. This evidence does not describe a world in which every dinosaur died on the day of impact. Many populations likely survived the first hours or weeks, only to encounter a planet whose light, temperature, vegetation, and food supply had changed beyond their ability to endure. The asteroid did not defeat the dinosaurs in a direct battle. It altered the rules of the world that had supported them. For more than 150 million years, non-avian dinosaurs occupied nearly every major terrestrial environment. Yet their dominance depended on conditions that could be dismantled by one brief encounter between Earth and an object from the dark. The dinosaur-killing impact made rock behave like liquid. For several terrifying minutes, the ground beneath the Chicxulub impact stopped behaving like the solid foundation you imagine rock must always be. When the asteroid struck the Yucatan region about 66 million years ago, the force drove a rapidly expanding shockwave through the crust and excavated a temporary cavity far deeper than the crater preserved today. Rock near the impact point was melted or vaporized, but the enormous movements farther outward cannot be explained by melting alone. Under the sudden stress, intense fracturing and vibration drastically reduced the strength of vast masses of crust, allowing rock that remained mostly solid to move in a fluid-like way. This temporary process is often described as rock fluidization. It did not turn granite into ordinary liquid water, nor did it allow the crust to remain soft afterward. Instead, broken and violently shaken rock briefly lost enough internal resistance to rise, spread, collapse, and slide across distances that would normally be impossible. Material from deep beneath the surface surged upward into an immense central peak, perhaps rising higher than the final crater rim, before gravity pulled it outward and downward. At the same time, the walls of the temporary cavity collapsed inward. These opposing movements formed the buried ring of mountains known as Chicxulub's Peak Ring. In 2016, scientists drilled into that structure beneath the Gulf of Mexico and recovered shocked, fractured granite that had originally been located much deeper in the crust. The samples contained abundant cracks and unusually high porosity, physical evidence that the impact had weakened and displaced the rock with extraordinary violence. Later research showed that the peak ring was built through dynamic collapse, rather than simply being a pile of material thrown upward and left where it landed. Within minutes, deeply buried rock had risen kilometers, traveled outward, and settled into a new landscape before regaining the strength expected of stone. The crater you would have seen after the event was therefore not merely a hole punched into Earth. It was the frozen remains of a brief interval when an entire region of crust moved almost like a collapsing sea. You trust rock because it appears to define permanence, yet Chicxulub reveals that solidity is conditional. Given sufficient energy, even the ground can forget its familiar shape, flow beneath forces no living body could survive, and harden again while preserving the direction of its impossible movement. Enormous volcanic eruptions were already changing Earth when the asteroid arrived. Before the asteroid appeared in the sky, Earth was already passing through one of the largest volcanic episodes of the last several 100 million years. In what is now western and central India, repeated eruptions were building the Deccan Traps, an immense province of stacked basalt flows created as magma rose through the crust and spread across the landscape. India was then an isolated landmass moving northward through the Indian Ocean, and the eruptions did not come from one familiar cone. Lava emerged from long fractures, sometimes covering enormous areas in successive sheets that cooled into the steppe-like terrain from which the word traps was derived. High-precision dating shows that Deccan volcanism occurred in major pulses before and after the Cretaceous-Paleogene boundary, with at least one interval of unusually rapid eruption beginning tens of thousands of years before the impact. The lava itself was only the visible part of the disturbance. Rising and intruding magma released carbon dioxide and sulfur-bearing gases, while heating surrounding rocks may have liberated additional compounds. Sulfur aerosols can temporarily reflect sunlight and cool the surface, whereas carbon dioxide can remain much longer and produce warming. Repeated pulses could therefore have subjected ecosystems to changing temperatures rather than one simple movement toward heat or cold. Evidence from ancient sediments and chemical climate indicators suggests that a significant warming episode occurred before the extinction boundary and was probably connected to early Deccan carbon release. Yet scientists must distinguish environmental stress from the main extinction trigger. Fossil patterns, climate modeling, ocean chemistry, and the abrupt timing of the biological collapse indicate that the Chicxulub impact was almost certainly the principal cause of the end Cretaceous mass extinction. Several studies find that Deccan volcanism alone does not reproduce the sudden global loss that followed the impact, although it may have altered climates beforehand and influenced the pace or character of recovery afterward. Researchers also continue debating exactly how much gas escaped, how rapidly it was released, and whether the impact changed the later tempo of the eruptions. The most accurate picture is therefore not a contest in which either an asteroid or volcanoes must be erased from the story. Earth was already being transformed by prolonged internal activity when an external catastrophe arrived almost instantly. Life near the end of the Cretaceous did not inhabit an untouched world that changed only on the day of impact. It lived beneath an atmosphere already responding to fire from below. The asteroid delivered the decisive blow, but it struck a planet whose climate and chemistry were not standing still, reminding you that the greatest turning points in nature may emerge when several histories, moving at completely different speeds, meet in the same narrow moment. Earth has survived several mass extinctions. The history of life is not a smooth climb toward the world you see today. It is a path repeatedly interrupted by doors that closed on entire branches of evolution. Paleontologists commonly recognize 5 especially severe crises during the last half-billion years: the End Ordovician, Late Devonian, End Permian, End Triassic, and End Cretaceous mass extinctions. These events are identified from unusually large and widespread losses recorded in fossils, but the phrase Big Five should not make them appear identical or perfectly separated from lesser crises. Some occurred in distinct pulses, some unfolded over longer intervals, and the completeness of the fossil record varies among environments and organisms. Their likely causes also differed: rapid climate change, major volcanic provinces, falling oxygen in the oceans, acidification, shifting sea levels, habitat loss, disrupted nutrient cycles, and, in the final case, a giant impact all played roles in different combinations. A mass extinction is not simply a period when many individual animals die. Death occurs constantly in healthy ecosystems. The defining change happens when species disappear far faster than new ones can evolve, across many regions and habitats, removing enough biological variety to dismantle established food webs. Survival is selective rather than fair. A species may endure because it can eat several kinds of food, reproduce rapidly, tolerate low oxygen, shelter underground, live across a wide geographic range, or simply occupy the right place when conditions change. Size, abundance, and former dominance offer no permanent protection. After a crisis, ecosystems do not immediately refill with the same organisms. Recovery can require millions of years as surviving lineages diversify, new relationships develop, and empty ecological roles are occupied in unfamiliar ways. The world that returns is not the world that was lost. Reef builders change, dominant predators disappear, once minor groups expand, and evolutionary possibilities that had been suppressed can suddenly open. Mammals, for example, did not appear only after the final great extinction, but the removal of many dominant terrestrial animals allowed surviving mammal lineages to diversify into roles that had previously been difficult to occupy. Saying that Earth survived these events is therefore true only from the perspective of the planet and life considered as a whole. Individual species did not survive in some collective sense. Most vanished permanently, taking unique bodies, behaviors, and evolutionary histories with them. Life continued, but continuity should not be confused with recovery without loss. Earth's resilience is real, yet it is indifferent to which organisms inherit the aftermath. You exist because earlier biospheres were repeatedly broken and rebuilt, but none of those rebuildings restored what came before. The fossil record offers no promise that life always returns in a familiar form. It offers a quieter and more unsettling lesson. Life can endure the destruction of a world, while the world known by its inhabitants disappears forever. The fossil record preserves only a tiny fraction of past life. Imagine every organism that has ever lived being reduced to a library, and then imagine discovering that almost every book was destroyed before anyone could read its title. Fossilization is not the normal fate of a dead organism. It is a rare interruption of decay. Most bodies are eaten by scavengers, broken apart by bacteria, dissolved by water, scattered by currents, or exposed to weather until nothing recognizable remains. Preservation usually requires an unusual sequence of events. Remains must reach a suitable environment, be buried quickly enough to escape destruction, survive chemical changes as sediment becomes rock, avoid being crushed or heated beyond recognition, return near the surface through erosion or uplift, and finally be found by someone before erosion destroys them again. Organisms with bones, teeth, shells, or woody tissues are therefore far more likely to enter the record than soft-bodied creatures, while animals living in rivers, lakes, shallow seas, and sediment-rich environments have better odds than those inhabiting mountains, rainforests, or other places where remains are rarely buried. Even behavior is preserved unevenly. A footprint, burrow, nest, or bite mark may survive when the body that created it disappears completely, allowing scientists to study an action without ever finding its maker. Exceptional sites known as Lagerstätten occasionally preserve feathers, skin outlines, stomach contents, delicate insects, and soft tissues, but their rarity shows how much information is normally lost. The record is also distorted by human access. Fossils buried beneath oceans, ice, cities, or inaccessible rock may exist without ever entering science. Paleontologists therefore do not treat the fossil record as a complete catalogue. They compare many locations, study sedimentary environments, measure preservation biases, and use living organisms, genetics, and geology to help fill gaps. A missing fossil does not prove that an organism never existed, but neither does every gap justify inventing an unknown creature. The challenge is to learn from an archive that is powerful precisely because it survived, yet incomplete because survival was never guaranteed. Every fossil in a museum represents not only a former life, but an extraordinary chain of accidents that protected one fragment while countless others vanished. What we call the history of life is therefore not the entire past laid open before us. It is the faint surviving outline left after decay, geology, and chance removed almost everything else. Most of Earth's earliest rocks have been destroyed. Earth is about 4.54 billion years old, yet almost no intact rock remains from its first several hundred million years. The missing record is not simply buried somewhere waiting to be uncovered. Much of it was physically transformed, mixed, melted, or broken into fragments so thoroughly that its original history can no longer be read as a complete rock sequence. The earliest Earth retained enormous internal heat, experienced major impacts, and possessed a crust that was repeatedly reworked by magma and mantle activity. Later, geological processes continued the erasure. Rocks exposed at the surface were weathered into sediment. Buried rocks were compressed and chemically altered. Deep heating caused metamorphism, and portions of old crust were remelted to produce younger rock. Tectonic recycling could drag material downward, mix it into the mantle, and eventually return some of its atoms through later volcanic activity without preserving the original landscape from which they came. This is why the oldest known intact terrestrial rocks are a little over 4 billion years old, while much older clues survive mainly as isolated mineral grains. Zircon is especially valuable because it is chemically durable and contains uranium when it crystallizes, but normally excludes lead, allowing scientists to date it through the lead produced by radioactive decay. Zircons from the Jack Hills of Western Australia reach ages of about 4.4 billion years, making them older than any complete rock that still surrounds them. They were eroded from their original source, transported, and deposited inside younger sedimentary rocks, like individual letters preserved after the book containing them was destroyed. Their chemistry can reveal clues about ancient magma and perhaps the presence of liquid water, but they cannot provide a full map of the vanished crust. Researchers also debate which processes dominated the destruction. Intense early impacts may have melted, buried, and mixed wide regions, while internal reworking and tectonic processes later altered what remained. Because the evidence is so fragmentary, reconstructions of the Hadean Earth must carry real uncertainty. The planet's earliest surface was not photographed in stone and stored intact beneath our feet. It was repeatedly rewritten using the same material until only resistant crystals and chemical signatures remained. Earth may remember its beginning, but it remembers it the way you might remember the earliest years of a life, through scattered fragments that survived while the complete scene disappeared beyond recovery. Scientists use meteorites to determine Earth's true age. The most reliable clock for Earth's birth was found not inside Earth, but in pieces of rock that fell from space. Scientists could date many terrestrial minerals, yet even extremely ancient samples revealed only when those particular minerals crystallized, not when the planet itself first assembled. Meteorites offered a different kind of evidence, because many are remnants of the same primitive material from which the planets formed. They developed during the solar system's earliest history, and, unlike Earth's crust, some remained relatively unchanged by oceans, weather, large-scale melting, and geological recycling. Researchers determine their ages through radioactive decay, a natural process in which unstable atoms transform into more stable products at measurable rates. Uranium is particularly useful because two of its naturally occurring forms decay through separate chains into different forms of lead. By measuring the proportions of uranium and lead isotopes in meteorites, and comparing samples that began with related chemical histories, scientists can calculate how much time has passed since those materials became closed systems. The method does not depend on watching atoms decay for billions of years. It depends on experimentally measured decay rates and the ratios preserved in the sample today. In the 20th century, geochemist Claire Patterson used lead isotopes from meteorites, including material associated with the Canyon Diablo meteorite, together with terrestrial lead measurements to calculate an age of approximately 4.55 billion years. Modern estimates place Earth's age near 4.54 billion years, with an uncertainty of only tens of millions of years. This number is not supported by one meteorite or one radioactive clock alone. Ages from different meteorite types, lunar samples, and the oldest minerals on Earth converge on the same early period, while the oldest calcium and aluminium-rich inclusions in meteorites show that the solar system began forming slightly before the fully assembled Earth. Scientists therefore distinguish between the first solid material in the solar system and the later process by which Earth accumulated through collisions. Meteorites are not assumed to be fragments of Earth, and their age is not simply copied onto the planet. They are used because Earth and meteorites belong to the same developing planetary system, preserving different parts of a shared beginning. The stones that struck Earth long after its formation carried clocks that our own active planet had largely erased. By reading them, humanity learned that the ground feels timeless only because your life occupies such a small interval of its history. The true age of your world was waiting in objects that had traveled through darkness while keeping the date of creation locked inside their atoms. Most of Earth's history passed before complex animals appeared. If Earth's entire history were compressed into a single day, complex animals would not appear until late in the evening. The planet formed about 454 billion years ago, yet the first widely accepted large and anatomically complex animals emerged only during the final several hundred million years of that immense span. For most of Earth's existence, life was microscopic. Early organisms were single-celled and lived in oceans that contained little oxygen, beneath an atmosphere with no animals, forests, grasslands, or familiar blue sky. These microorganisms were not merely waiting for complex life to begin. They were already transforming the planet. Cyanobacteria released oxygen through photosynthesis. Other microbes cycled carbon, sulfur, and nitrogen, and generations of tiny cells gradually altered the chemistry of the oceans and atmosphere. Cells with internal structures appeared later, followed by simple multicellular organisms. But large animals required more than cells simply joining together. They needed ways to coordinate growth, move nutrients, communicate between tissues, reproduce reliably, and build bodies that could survive in changing environments. Rising oxygen levels may have helped by making more energy available, while ecological competition, predation, genetic innovation, and environmental change probably contributed as well. By roughly 575 million years ago, the Ediacaran seas contained strange soft-bodied organisms, many unlike anything alive today. Then, beginning around 541 million years ago, the Cambrian period preserved a remarkable expansion of animal forms with eyes, shells, limbs, mouths, and increasingly complex behavior. This was not the sudden creation of animal life from nothing. It was the visible result of evolutionary developments whose earlier stages are difficult to reconstruct. More than 80% of Earth's history had already passed before these recognizable animal ecosystems appeared. Dinosaurs, mammals, birds, and humans arrived much later still, occupying only the final sliver of planetary time. You naturally imagine the history of Earth through creatures with faces, movement, and bones, because those are the forms easiest to notice, but the deeper history belonged to lives too small to see. Complex animals are not the main story of Earth measured by duration. They are a recent chapter made possible by billions of years, during which invisible organisms quietly prepared a planet they would never live to witness. Day on the early Earth lasted far less than 24 hours. Long before clocks divided your life into 24 hours, sunrise returned much sooner than it does today. A day is simply the time Earth takes to complete one rotation, and that rotation has never been perfectly fixed. The young Earth almost certainly spun much faster, although scientists cannot assign one exact day length to its earliest period because the planet's formation was violent and the available evidence becomes increasingly fragmentary with age. Models suggest that after the moon-forming era, a day may have lasted only a fraction of its modern length, possibly closer to 10 hours during parts of Earth's youth. By about 1.4 billion years ago, some reconstructions indicate a day of roughly 19 hours, while much younger geological evidence shows it continuing to lengthen toward the value you know. Scientists read this lost time in rocks. Certain tidal sediments preserve repeating layers, created by daily and monthly changes in currents, allowing researchers to count ancient cycles. Fossil corals and shells can also contain microscopic growth bands linked to daily and seasonal rhythms. Some ancient corals record more days within a year than occur today, not because the year was dramatically longer, but because each day ended sooner. The main cause of the long-term slowdown is tidal friction. The moon's gravity raises tidal bulges in Earth's oceans, and because Earth turns faster than the moon travels around it, those bulges are carried slightly ahead. Their gravitational interaction removes a tiny amount of rotational energy from Earth. Continents, ocean depth, coastlines, ice, and the arrangement of seas influence how efficiently this happens, so the day has not lengthened at one perfectly constant rate. Atmospheric winds, major currents, changes in ice, and movement inside the planet also cause smaller short-term variations, sometimes making individual days slightly longer or shorter. The 24-hour day is therefore not a timeless rule built into nature. It is the present pace of a rotating world that has been slowing for billions of years. Ancient life experienced more sunrises within each orbit of the sun, and future life will experience fewer. The day feels like the fixed container of your existence, yet it is itself changing, stretched almost imperceptibly by forces operating between Earth, its oceans, and the sky. The moon is slowly moving away from Earth. The moon is leaving Earth, not suddenly enough to notice in the night sky, but steadily enough for scientists to measure from the surface of another world. Its average distance is increasing by about 3.8 centimeters each year, roughly the rate at which human fingernails grow. This motion has been measured with lunar laser ranging, a technique that uses reflector arrays placed on the moon by Apollo astronauts and Soviet robotic missions. Observatories on Earth send brief laser pulses toward these reflectors and measure how long the light takes to return, allowing the Earth-Moon distance to be tracked with extraordinary precision. The cause lies in the interaction between the moon's gravity and Earth's oceans. Lunar gravity raises tides, but Earth rotates so quickly that the tidal bulges are carried slightly ahead of the moon's position. Those displaced bulges exert a small gravitational pull on the moon, giving it orbital energy and causing it to move into a wider orbit. The moon does not climb outward in a straight line. Its orbit remains elliptical and is continuously influenced by the sun and the uneven distribution of mass within both worlds. The present rate of retreat has also not remained constant throughout history. The positions of continents, shapes of ocean basins, water depth, and efficiency of tidal dissipation have changed repeatedly, sometimes strengthening the transfer of energy and sometimes weakening it. Geological tidal records show that the moon was considerably closer in the distant past, appearing larger in the sky and producing different tidal rhythms. Its retreat also means that total solar eclipses are temporary features of Earth's history. Today, the moon and sun happen to appear nearly equal in size from the surface, allowing the lunar disk to cover the sun completely. Hundreds of millions of years from now, a more distant moon will usually appear too small to create the same kind of total eclipse. The moon will not simply escape Earth in the foreseeable future, and the sun's own evolution will transform the system long before an ideal final tidal balance could be reached. Still, every laser measurement confirms that the relationship is changing. The moon seems like the most dependable object in the night, returning through familiar phases, yet each orbit places it almost invisibly farther away. Even the oldest companion in the human sky is not standing still. It is carrying part of Earth's lost rotation outward, centimeter by centimeter into the darkness. Earth's rotation is gradually slowing down. The sunrise is arriving later than it would have on a younger Earth, not by an amount you can notice, but by enough for ancient eclipses to reveal the difference. Over very long periods, Earth's rotation has gradually slowed, causing the average length of the day to increase. The clearest long-term cause is tidal friction. As the oceans move across coastlines and the seafloor under the gravitational influence of the moon, and more weakly, the sun, part of Earth's rotational energy is converted into heat. The effect is extraordinarily small from one day to the next, yet it accumulates across centuries and geological ages. Historical astronomers unknowingly preserved evidence of this change when they recorded where and when eclipses appeared. If Earth had always rotated at today's exact rate, some ancient eclipses would have crossed different regions from those described in Babylonian, Chinese, and Arabian records. By comparing those accounts with modern orbital calculations, researchers can estimate how Earth's rotation has changed across thousands of years. The average long-term increase in day length is commonly placed at roughly a couple of milliseconds per century, but the rate is not perfectly steady. Ocean basins change shape, continents move, ice sheets grow and melt, and the mantle slowly adjusts after the removal of ancient ice. These processes redistribute mass and can partly accelerate or oppose the general slowdown. The result is not a simple clock losing the same amount every year, but a rotating planet responding to everything moving within and around it. Even so, the long view remains clear. Ancient Earth completed more rotations during one journey around the Sun than modern Earth does. Far in the future, days will be slightly longer still, though no human life will experience the difference directly. The 24-hour cycle feels like one of nature's permanent rules because your entire existence has been organized within it. Yet it is only the current rhythm of a world gradually surrendering part of its spin. Time as measured by Earth is not flowing beside the planet. It is being shaped by the planet's physical motion, and the length of a day is slowly changing beneath every clock that pretends otherwise. The length of a day is never exactly constant. Midnight does not return after precisely the same amount of planetary rotation every day, even though your clock is designed to behave as though it does. Modern timekeeping defines a standard day as exactly 86,400 atomic seconds, but the real Earth speeds up and slows down by tiny, irregular amounts. The differences are usually measured in fractions of a millisecond, far too small to affect sleep, sunrise plans, or ordinary watches, yet large enough to matter for astronomy, spacecraft navigation, satellite positioning, and systems that must know Earth's exact orientation in space. Much of this variation comes from the atmosphere. When powerful winds change speed or direction, they exchange angular momentum with the solid planet beneath them. If the atmosphere gains a little rotational motion, the ground may rotate slightly more slowly. When the atmosphere loses it, the solid Earth may gain it back. Ocean currents, seasonal changes in pressure, and the movement of water between oceans and continents produce similar exchanges. During different parts of the year, winds and currents reorganize enough to create measurable seasonal patterns in the length of day. Slower changes can also come from motion within Earth, including interactions between the mantle and the fluid core. Scientists track these variations using several methods, especially very long baseline interferometry, in which radio telescopes located far apart observe distant quasars and determine Earth's rotational angle with extraordinary precision. The rotation-based timescale called UT1 therefore drifts relative to uniform atomic time because one follows the actual planet while the other follows the steady vibration of atoms. This is why civil time has historically required occasional adjustments, although the rules governing future leap seconds are changing. Some modern days have been slightly shorter than the standard 24 hours, even while Earth continues its broader long-term slowdown. That is not a contradiction. A person walking gradually downhill can still take a few steps upward, and Earth's rotation behaves with the same layered complexity, a long trend carrying countless shorter variations within it. The day you experience as a clean block on a calendar is therefore a useful human construction placed over a restless physical event. Every rotation is almost the same as the last, but never perfectly identical, because the planet is continually exchanging motion among its air, oceans, land, and hidden interior. Earth's axis wobbles over thousands of years. The northern sky will not always revolve around Polaris, because Earth's axis is slowly drawing an enormous circle among the stars. This motion is called axial precession, and it resembles the gradual wobble of a spinning top, whose axis changes direction while the top itself continues rotating. Earth is slightly wider around the equator than from pole to pole, and the gravitational pulls of the Moon and Sun act on this equatorial bulge. Their combined influence does not quickly tip the planet over. Instead, it causes the direction of the rotational axis to shift slowly through space. One complete precessional cycle takes roughly 26,000 years. The angle of Earth's tilt remains broadly similar during this particular motion, but the direction in which that tilted axis points changes. Polaris happens to lie close to the northern celestial pole today, making it a useful guide for navigation. Yet it has not always held that role and will not keep it forever. Thousands of years from now, other stars will lie nearer the pole, while the star patterns surrounding the axis will appear to turn around a different center. Precession also changes where Earth is in its orbit when each season occurs. Today, the northern hemisphere experiences winter when Earth is relatively close to the Sun, but precession gradually shifts that relationship. By itself, this does not create a simple global warming or cooling switch, because the effects differ between hemispheres and interact with changes in orbital shape and the angle of Earth's tilt. Together, these long cycles influence how sunlight is distributed across latitudes and seasons, helping pace major climate changes over tens of thousands of years. Smaller motions called nutations are layered on top of the main precessional circle, caused largely by variations in the Moon's orbit, while much shorter wobbles move the rotation axis slightly across Earth's own surface. These are related motions, but they are not the same phenomenon. Axial precession is the slow redirection of the entire spin axis against the background of space. Human beings once treated the stars as the ultimate image of permanence. Yet even the point around which the heavens appear to turn is temporary. The sky changes too slowly for one lifetime to witness its full motion. But ancient monuments, old astronomical records, and modern calculations reveal that Earth has been quietly turning its axis through the cosmos, carrying every future generation beneath a slightly different north. The Moon may prevent Earth's tilt from becoming far more chaotic. Remove the Moon from Earth, and the planet would not immediately fall sideways, but the angle of its rotation could become much less predictable over geological time. Earth's axis is tilted by about 23 degrees relative to its path around the Sun, giving different latitudes changing amounts of sunlight through the year. That tilt is influenced by the gravitational pulls of other planets, especially Jupiter and Saturn, which slowly alter Earth's orbit and can disturb the direction of its spin. The Moon helps by exerting a strong gravitational torque on Earth's slightly swollen equatorial region, causing the spin axis to respond at a rate that generally avoids dangerous resonances with those slower orbital disturbances. A resonance would occur if different cycles began reinforcing one another, allowing small changes to grow into much larger variations. Classic computer simulations found that without the Moon, Earth's tilt might wander chaotically across an enormous range, potentially shifting between nearly upright and severely tilted states. Such changes would radically redistribute sunlight. Polar regions could receive intense seasonal heating, tropical regions could experience unfamiliar darkness and cold, and climate zones might repeatedly migrate across continents. Yet the story requires caution. Later research has shown that a moonless Earth would not necessarily experience every possible extreme, because the outcome depends on its rotation speed, the arrangement of the other planets, and how the system evolves through time. The Moon should therefore not be described as a perfect lock-holding Earth at one angle. Our tilt still changes, and the Moon itself is moving gradually farther away, weakening its stabilizing influence over immense periods. What it provides is something subtler. It changes the rhythm of Earth's response, reducing the likelihood that small planetary tugs will combine into much larger and more chaotic swings. Complex life did not arise because the Moon deliberately protected the climate, and stable tilt alone cannot guarantee habitability, but the lunar influence may have made Earth's long-term environment less erratic than it otherwise would have been. The familiar Moon is usually treated as a light in the night or a marker of months, yet its deeper role may be almost invisible. By pulling continuously on the spinning planet, it may have helped keep Earth from leaning unpredictably through space, allowing climates to change within limits that life had time to follow. Magnetic north can move by dozens of kilometers in a year. A compass pointing north is following a destination that can travel farther in 1 year than many people commute in a lifetime. Magnetic north is not the same as the geographic North Pole, and it is not a permanent spot fixed beneath the Arctic ice. It is commonly defined as the region where Earth's magnetic field points vertically downward, leaving almost no horizontal field for a compass needle to follow. This means an ordinary compass actually becomes less useful as it approaches the magnetic pole, because there is no strong horizontal direction there to indicate where north lies. When James Clark Ross located the pole in 1831, it was in the Canadian Arctic. During the 20th century, it continued drifting, and around the 1990s, its movement accelerated dramatically toward the central Arctic and Siberia. By the early 21st century, it was traveling at roughly 50 kilometers per year. The newest world magnetic model indicates that this rapid motion has recently slowed to around 35 kilometers per year, still fast enough for navigation models to require regular updates. The pole moves because Earth's magnetic field is not produced by one rigid bar magnet. Changes in the flow of conductive material deep inside the planet alter the shape and strength of the field measured at the surface. Small adjustments far below can therefore shift the place where the field becomes vertical by dozens of kilometers above. Solar activity adds shorter disturbances, causing the observed magnetic pole region to trace irregular paths over a day rather than occupying one mathematical point at every moment. This moving target matters because aircraft, ships, submarines, drilling operations, military systems, and many electronic compasses depend on magnetic declination, the difference between magnetic north and true north at a particular location. The world magnetic model is updated to predict how that difference will change, but it remains a forecast of a field that can behave unexpectedly. Even the phrase, "a compass points toward the magnetic pole," is an oversimplification. The needle follows the local direction of the field, which is curved and irregular, rather than aiming along a perfect line toward one Arctic coordinate. North feels like the most basic direction, the starting point from which every map is organized. Yet magnetic north is not a fixed command written onto Earth. It is a moving consequence of processes hidden far below, and every compass is quietly responding to a planet whose invisible geography is being redrawn while you travel across it. The geographic North Pole does not stay in one exact place. Even true north is not nailed permanently to one point on the ground. The geographic North Pole is usually described as the place where Earth's rotational axis meets the surface. But the real rotation axis does not pass through exactly the same location in the crust every day. Instead, its intersection wanders across an area measuring several meters, producing a motion that scientists call polar motion. One major component is the Chandler wobble, a natural oscillation lasting about 14 months. Another follows an annual pattern caused by seasonal movements of air, water, snow, and ice. When mass shifts between continents and oceans, Earth must slightly readjust the position around which it spins. Just as an unevenly loaded rotating object changes its balance, atmospheric winds and ocean currents contribute additional motion, while slower effects arise as the mantle continues responding to the disappearance of massive ice sheets from the last glacial period. Modern ice loss and changes in groundwater storage can also alter the longer-term direction of the pole's drift. Since precise observations began, the instantaneous rotational pole has moved as far as roughly 12 meters from its average position. This is far too little to shift climate zones, move borders, or make explorers suddenly stand in a different country. But it is large enough to matter for satellite navigation, astronomical observatories, spacecraft tracking, and measurements requiring centimeter-level accuracy. Scientists monitor the motion using networks of radio telescopes observing distant quasars, satellite laser ranging, global navigation systems, and other geodetic techniques. International reference systems still define a stable conventional pole, so maps and coordinates do not have to be rewritten every day, but the physical axis continues wandering around that reference. This motion must not be confused with magnetic north, which can travel tens of kilometers in a year, or with the much slower change in the direction of Earth's axis against the stars. Polar motion occurs within Earth itself as the rotational axis shifts relative to the crust beneath you. A globe in a classroom spins around a perfectly centered rod because simplicity makes the model useful. The real planet has no such rod. It balances itself continuously while oceans circulate, seasons move water and air, ice disappears, and the deep interior adjusts. Geographic north is therefore both a reliable idea and a moving physical location. Fixed enough to organize the world, yet restless enough to reveal that even the axis of Earth must respond to everything the planet carries. An underwater landslide can create a tsunami without a major earthquake. a coastline can be struck by a devastating tsunami, even when no enormous earthquake has occurred beneath the ocean. The hidden cause may be a submarine landslide, in which a vast mass of sediment, broken rock, or volcanic debris suddenly collapses down an underwater slope. Continental margins often collect thick layers of sediment delivered by rivers and currents, and these deposits can remain in place for centuries while becoming increasingly unstable. A moderate earthquake may provide the final push, but failure can also be encouraged by rapid sediment accumulation, erosion at the base of a slope, volcanic activity, changes in pressure within buried fluids, or the gradual weakening of sediment. Once the material begins moving, it can accelerate downslope and displace water both ahead of it and above the empty space it leaves behind. That rapid displacement creates waves capable of reaching nearby shores with very little warning. Unlike many earthquake-generated tsunamis, which begin across broad sections of seafloor and can cross entire ocean basins, landslide tsunamis are often more concentrated. Their largest waves may strike a limited stretch of coastline, while places farther away receive much smaller waves, making the disaster harder to predict from earthquake magnitude alone. The 1998 tsunami in Papua New Guinea demonstrated this danger. The earthquake that preceded it was not large enough to explain the extreme local wave heights, and investigations concluded that an earthquake-triggered submarine landslide was the most likely source of the destructive tsunami that arrived only minutes later. Ancient deposits also preserve the memory of the Storegga slide, an enormous collapse off Norway roughly 8,000 years ago that sent waves across parts of the North Atlantic. Scientists search for old landslide scars using sonar maps, sediment cores, and seismic images of layers beneath the seabed, but many unstable slopes remain poorly mapped. Warning systems designed mainly around major earthquakes may also struggle when a smaller seismic event triggers a much larger underwater collapse. The sea does not care whether its displacement begins with a famous fault or a silent slope giving way in darkness. A mountainside can fall where no human eye can see it, and the first visible evidence may be the ocean rising against a distant shore. Magma chambers are not giant underground lakes of liquid fire. Beneath most volcanoes, there is no enormous empty cavern filled from wall to wall with glowing liquid rock. The familiar image of a magma chamber as a fiery underground lake is useful for simple diagrams, but modern evidence suggests that many volcanic reservoirs resemble vast zones of hot crystalline material containing melt between tightly packed mineral grains. Geologists often call this a crystal mush. In such a system, much of the reservoir may be solid crystals, while liquid magma occupies pores, lenses, channels, and isolated pockets within the framework. The proportion of melt can change from place to place, and only some regions may contain magma fluid enough to move rapidly or erupt. This explains why detecting a large, low-velocity zone beneath a volcano does not mean that the entire volume is ready to burst onto the surface. Seismic waves slow in hot, partially molten rock, but converting those measurements into an exact amount of liquid is difficult. Electrical methods can detect areas containing connected melt and fluids, while crystals carried out during eruptions preserve chemical layers, showing that they grew through changing temperatures and repeated injections of new magma. These records reveal reservoirs that are continually assembled, cooled, mixed, reheated, and reorganized rather than filled once like a tank. Fresh, hotter magma rising from below can enter a crystal-rich region, supply heat and gases, and allow pockets of melt to connect. In other cases, melt may separate from the mush and accumulate in a smaller, more mobile body shortly before an eruption. Some reservoirs remain largely locked for thousands of years, and eventually cool into solid, intrusive rock without producing a major eruption at all. The ancient remains of such systems can later be exposed by erosion as plutons, giving geologists a frozen view of structures that once existed beneath volcanoes. Even the term chamber can be misleading because a volcanic plumbing system may include several storage regions at different depths. linked temporarily by fractures rather than one permanent central room. A volcano is therefore not sitting above a simple lake waiting to overflow. It rests above a changing network in which crystals, melt, gas, heat, and rock continually negotiate how much material can move. The dramatic eruption at the surface may last days, but the magma feeding it may have spent centuries being assembled inside a reservoir that was mostly solid until conditions changed. Volcanic lightning can fill an ash cloud with electrical storms. An erupting volcano can manufacture its own thunderstorm before any ordinary storm cloud arrives. During an explosive eruption, expanding gas tears magma into countless pieces and launches ash, rock fragments, and vapor upward in a turbulent column. Near the vent, particles collide, fracture, and rub against one another, transferring electrical charge in processes related to fragmentation and contact between grains. Smaller and larger particles can acquire different charges, and the violent motion of the plume separates them faster than the charge can quietly recombine. When the electrical difference between regions becomes strong enough, the air breaks down and a discharge flashes through the ash. Higher in the atmosphere, the plume may cool enough for water droplets and ice particles to form. Collisions among ice, ash, and frozen particles can then create a second style of electrification, resembling the charge separation inside powerful weather thunderstorms. This means one eruption can produce different electrical regions at different heights. Short, frequent discharges near the vent, and larger lightning flashes across the rising or spreading cloud. Not every eruption creates a spectacular electrical display. The amount of ash, particle sizes, water content, plume height, eruption intensity, and surrounding weather all influence whether charge can build and separate efficiently. When conditions align, however, the result can be extraordinary. The January 2022 Hunger eruption in Tonga produced nearly 200,000 detected lightning flashes, with the most intense phase exceeding 2,600 flashes in a single minute, making it the most intense lightning activity yet recorded. Volcanic lightning is more than a dramatic visual effect. Radio and satellite networks can detect electrical discharges through darkness and thick cloud, sometimes providing rapid confirmation that an ash-rich eruption is underway when the volcano itself cannot be seen. Flash rates and locations can also help scientists estimate changes in plume behavior, identify sustained ash production, and improve warnings for aircraft. The lightning can start fires, damage equipment, and add another hazard to an eruption already filled with ash and falling debris. But it also turns the plume into a signal that can be followed from far away. An ash cloud may look like nothing more than rock reduced to dust. Yet within that darkness, billions of collisions are sorting invisible charge until the cloud illuminates itself, briefly revealing the violence taking place inside. Lightning can become hotter than the surface of the sun. For a few millionths of a second, an ordinary thunderstorm can create a channel of air far hotter than the glowing surface of the sun. A strong lightning return stroke may heat the narrow path around it to roughly 30,000 degrees Celsius, while the sun's visible surface is about 5,500 degrees. This comparison is scientifically accurate, but it does not mean lightning contains more total heat or energy than the sun. The lightning channel is only a few centimeters wide, exists for an extremely brief time, and heats a tiny amount of air, whereas the sun maintains enormous temperatures across a sphere more than 1 million kilometers wide. Lightning begins when collisions among ice crystals, water droplets, and soft hail inside a turbulent thundercloud separate electrical charge. Different regions of the cloud become increasingly positive or negative, while the ground below can develop an opposing charge. Air normally acts as an electrical insulator, but when the difference becomes intense enough, branching paths of partially ionized air begin advancing through the atmosphere. If a descending channel connects with an upward-reaching channel from the ground, a powerful current races along the completed path. This return stroke is the brilliant flash you usually recognize as lightning. Its sudden heating transforms the surrounding air into plasma, a state in which electrons are separated from atoms and the gas becomes electrically conductive. The heated air expands so violently that it creates a shock wave. As that disturbance travels outward and weakens, you hear it as thunder. The sharp crack comes from a nearby part of the channel, while the longer rumble arrives because sound from different bends and branches reaches you at different times. The bolt does not remain at its peak temperature long enough to set the entire sky on fire, but it can melt sand into glassy structures, split trees as moisture inside them rapidly expands, ignite buildings, and damage living tissue by forcing current through the body. The strange lesson is not simply that lightning becomes hotter than the sun's surface. It is that temperature describes how intensely particles are moving in one place, not how much energy an entire object contains. A thread of air can briefly become hotter than a star and still fade before your eyes have fully registered it, leaving only a white scar across the sky and a delayed sound announcing that the atmosphere has returned to its ordinary state. Enormous electrical flashes occur high above thunderstorms. Some thunderstorms send light upward into regions where the sky is almost space, producing electrical shapes so large that a single flash can stretch across tens of kilometers. These events are known collectively as transient luminous events, and they occur high above the familiar lightning hidden inside or below a storm. Pilots reported strange red flashes for decades, but the phenomenon was largely dismissed until a low-light camera accidentally recorded one in 1989. Scientists now know that the upper atmosphere can produce several distinct forms. Sprites are usually red, extremely brief structures appearing roughly 50 to 90 kilometers above the ground. Some resemble enormous jellyfish with a bright upper region and delicate tendrils extending downward, while others form columns or branching shapes. They often follow particularly powerful cloud-to-ground lightning strokes that rapidly rearrange electrical charge inside a storm. That change creates an electric field far above the cloud, where the air is thin enough for electrons to accelerate and collide with nitrogen molecules, causing the atmosphere to glow red. Elves are different. They appear as rapidly expanding rings near the lower edge of the ionosphere and may spread across hundreds of kilometers in less than 1,000th of a second. They are produced when an intense lightning pulse sends electromagnetic energy upward and briefly excites the thin air. Blue jets begin near thunderstorm tops and rise upward as narrow blue cones, while gigantic jets can extend from the cloud toward the ionosphere, creating a rare electrical connection between weather below and the charged layers above. These events are not simply inverted lightning bolts, and they do not all arise through the same mechanism. Their color, shape, height, and duration depend on air density, atmospheric chemistry, storm structure, and the kind of electrical disturbance that initiated them. They are difficult to observe because clouds can hide the storm below. The flashes may last only milliseconds, and a person must often watch from far enough away to see above the horizon. Cameras on mountains, aircraft, satellites, and the International Space Station have gradually revealed how common and diverse they can be. Scientists are still investigating how they influence the upper atmosphere and Earth's wider electrical circuit. A thunderstorm therefore occupies more of the sky than its dark cloud suggests. Long after its top appears to end, invisible fields continue upward, sometimes illuminating the edge of space with red branches, blue fountains, and expanding rings that vanish almost as soon as the atmosphere allows them to exist. Atmospheric rivers can carry more water than major rivers on the ground. River wider than a city and longer than many countries can cross the sky without containing a single visible channel of flowing liquid. Atmospheric rivers are long, relatively narrow corridors of concentrated water vapor, transported through the lower atmosphere by strong winds. They often draw moisture from warm ocean regions and carry it toward higher latitudes as part of large weather systems. An average atmospheric river can move an amount of water vapor comparable to the flow of the Mississippi River at its mouth, while a powerful one may transport roughly 7.5 to 15 times as much. This does not mean a liquid river is suspended above the ocean. The water remains mainly as invisible vapor distributed through a deep band of moving air, and the comparison describes how much water crosses an imaginary line each second. Atmospheric rivers commonly form ahead of cold fronts, where winds concentrate moisture into corridors often several hundred kilometers wide and more than 1,000 kilometers long. While they remain over open water, they may look from below like little more than a broad field of cloud. Their importance becomes clear when they reach land. Mountains force the moist air upward, causing it to cool and condense into rain or snow. A well-positioned atmospheric river can replenish reservoirs, build mountain snowpack, end drought conditions, and supply a large share of a region's annual precipitation in only a few events. Along the western United States, atmospheric rivers provide roughly 30 to 50% of yearly rain and snow in many areas. Yet the same system can become destructive when it is unusually strong, arrives after the ground is already saturated, stalls over one watershed, or melts existing snow with warm rain. Rivers can rise rapidly, hillsides can fail, roads can disappear beneath floodwater, and communities far from the coast can be affected as moisture is carried inland. Meteorologists track these systems with satellites, ocean buoys, radar, weather balloons, aircraft instruments, and computer models that estimate both the amount of vapor and the strength of the winds transporting it. Forecasting remains difficult because a modest shift in the path can determine whether the heaviest precipitation falls into a reservoir, across a mountain range, or above an inhabited valley. Atmospheric rivers are therefore neither naturally good nor naturally disastrous. They are essential parts of the water cycle whose effects depend on timing, intensity, geography, and preparedness. The rivers you can see are only the final receivers. Before water rushes through their channels, much of it may have traveled thousands of kilometers through the air, carried by a current with no banks, and revealed only when the sky finally lets it fall. A hurricane is a heat engine, powered by warm ocean water. A hurricane is not simply a violent collection of clouds. It is an enormous atmospheric engine that keeps running only while the ocean continues supplying its fuel. The process begins over warm tropical water, usually when the upper ocean is warm through a sufficient depth, rather than heated only at its surface. Seawater evaporates, adding invisible moisture to the air just above it. When that warm, humid air rises, the pressure below decreases and more air flows inward to replace it. As the rising water vapor cools and condenses into cloud droplets, it releases stored heat into the surrounding atmosphere. That heat makes the air more buoyant, encouraging it to rise farther and draw in still more moisture from below. A self-reinforcing cycle can develop. Evaporation feeds rising air, condensation releases heat, and the strengthening circulation pulls additional energy from the sea. Earth's rotation turns the inward-moving air, helping the storm organize into spiral rain bands around a central region. If conditions become favorable enough, air descends inside the center and creates the eye, an area that may appear strangely calm, while the eye wall surrounding it contains the strongest winds and most intense rainfall. Warm water alone, however, cannot produce a hurricane. The storm also needs a pre-existing atmospheric disturbance, abundant moisture, enough distance from the equator for planetary rotation to influence the flow, and relatively low differences in wind speed and direction with height. Strong upper-level winds can tilt the circulation apart before it becomes organized. A hurricane also does not drink unlimited energy from the ocean without changing it. Powerful winds stir colder water upward and leave a cooler trail behind, sometimes weakening the storm's own fuel supply. Once the system moves over land, crosses colder water, or encounters dry air and disruptive winds, its engine begins losing the conditions that maintained it. The phrase heat engine therefore describes more than a metaphor. The storm absorbs energy from a warm source below, converts part of that energy into organized motion, and releases heat high in the atmosphere as water condenses. Yet the conversion is never perfectly efficient, and the path of each storm depends on a delicate arrangement of ocean and air. What you see from space as a beautiful spiral is a structure continuously rebuilding itself from evaporated seawater, surviving only while the environment keeps paying its enormous energy cost. The ozone layer is both a shield and a dangerous pollutant, the same molecule that protects your skin high above. Earth can damage your lungs when it forms near the ground. Ozone consists of 3 oxygen atoms, but its effect depends less on what it is than on where it exists. Most atmospheric ozone is concentrated in the stratosphere, generally between about 15 and 40 kilometers above the surface. There, sunlight continually creates and destroys ozone through natural chemical cycles. Ordinary oxygen molecules absorb energetic ultraviolet light and can split into individual oxygen atoms. Those atoms may then combine with other oxygen molecules to form ozone. Ozone absorbs much of the sun's harmful ultraviolet radiation, especially the band known as ultraviolet B, preventing a larger amount from reaching living tissue at the surface. Without this thin and chemically active shield, damage to DNA would increase, raising risks for skin cancer and cataracts while harming crops, marine organisms, and ecosystems. Human-made chemicals, once used widely in refrigeration, aerosols, foams, and fire suppression, released chlorine and bromine after reaching the stratosphere, allowing a single reactive atom to participate in repeated ozone-destroying reactions. International restrictions greatly reduce many of these substances, showing that atmospheric damage can be slowed when its chemical cause is understood and addressed. Near the ground, however, ozone becomes part of a very different story. It is usually not emitted directly from a vehicle, factory, or wildfire. Instead, sunlight drives reactions between nitrogen oxides and volatile organic compounds released from combustion, fuels, industrial activity, vegetation, and other sources. The resulting ozone can travel away from the place where its ingredients were produced, creating unhealthy air even in areas without obvious pollution nearby. When inhaled, it reacts with tissues lining the respiratory system, causing inflammation, coughing, chest discomfort, reduced lung function, and worsening symptoms in people with asthma or other respiratory conditions. It can also enter plant leaves, damaging cells and reducing growth. Calling ozone either good or bad is therefore incomplete. High above you, it intercepts radiation before that radiation can reach life. Near your breathing zone, its chemical reactivity turns against the same living tissues. Nature has not changed the molecule between those two places. Distance alone changes its role, revealing that protection and poison can be made from the same substance when the atmosphere places it on opposite sides of the world's most important boundary. Most of the air above you lies within a small distance of the surface. The sky appears to rise without limit, yet nearly all the air pressing on your body is crowded into the first small fraction of that apparent height. Earth's atmosphere does not end at one sharp boundary. Traces of gas extend hundreds of kilometers upward and gradually blend into space. But gravity continually pulls molecules toward the planet, compressing the lower atmosphere beneath the weight of everything above it. As a result, air density and pressure are greatest near sea level and fall rapidly with altitude. Roughly 80% of the atmosphere's mass lies within the troposphere, the lowest layer, which averages only about 12 kilometers in depth, and around 99% of all air remains below an altitude of approximately 30 kilometers. This means the vast regions occupied by the mesosphere, thermosphere, and exosphere contain only a tiny fraction of the atmospheric mass, even though they cover enormous distances. The concentration near the surface explains why altitude affects the human body so quickly. The proportion of oxygen in ordinary dry air remains close to the same at mountain height, but the total pressure decreases, so each breath contains fewer oxygen molecules. Your lungs must work with thinner material, your heart may beat faster, and prolonged exposure requires biological adjustment. Aircraft flying at high altitude must pressurize their cabins, not because oxygen has vanished from the surrounding air, but because the molecules are too widely separated for human lungs to obtain enough of them at normal breathing pressure. Weather is also concentrated near the ground because the lower atmosphere contains nearly all atmospheric water vapor and most of the aerosols around which cloud droplets can form. Above that active layer, The air becomes so sparse that a region can still possess extremely energetic individual particles while containing too little matter to feel hot against a human body in the ordinary sense. Air pressure at the surface is therefore not produced by an invisible force pushing downward from nowhere. It is the combined weight of the atmospheric column held by gravity above every patch of land and water. You do not notice this load because the fluids and gases inside your body push outward in balance with it. The atmosphere feels vast because you look upward through it. But mass tells a different story. Human civilization, weather, breathing, clouds, and nearly every familiar interaction with air occur inside a narrow lower layer hugging the ground. The open sky is visually immense, yet the breathable world is gathered close to Earth, as though gravity has pressed almost the entire atmosphere into the small space where life happens to need it. Tides do not only move the oceans, they also move the solid ground. While you stand on land believing the moon is pulling only at distant seas, the ground beneath your body is quietly rising and falling with it. The gravitational attractions of the moon and the sun act on the entire Earth, not only on water, producing deformations known as solid earth tides or body tides. Rock feels rigid on the scale of a hand or a building, but the planet is large enough to respond elastically to these slowly changing forces. As Earth rotates beneath the moon, one region of the crust is gently stretched outward, later relaxes, and then moves through another part of the repeating cycle. Depending on location and the alignment of the moon and sun, the vertical movement can reach several centimeters and, under favorable conditions, considerably more. You do not feel yourself being lifted because the motion is gradual, spread across a vast region and shared by the landscape, buildings, roads, and nearly everything around you. There is no sudden acceleration to alert your senses. Highly sensitive instruments notice it clearly, however. Satellite positioning stations, gravimeters, strain meters, and tilt meters must account for these predictable movements when measuring volcanic swelling, fault deformation, groundwater changes, or the slow motion of continents. Without correcting for Earth tides, a scientist might mistake the moon's routine pull for a sign that magma is accumulating or that the crust is undergoing a new kind of stress. The effect also changes gravity slightly because the observer's distance from Earth's center and the distribution of nearby mass both vary through the tidal cycle. Solid Earth tides can alter stresses on faults and volcanic systems by small amounts, but they do not normally create earthquakes or eruptions on their own. At most, in a system already extremely close to failure, tidal stress may help influence the precise timing of a small number of events, and even that relationship is subtle rather than a dependable prediction tool. The important revelation is quieter. Solidity does not mean perfect stillness. The land beneath your feet is continually breathing in response to bodies hundreds of thousands or millions of kilometers away, stretching toward the moon, responding more faintly to the sun, and returning toward its former shape as the geometry changes. An ocean tide announces itself along a shoreline, but a land tide carries forests, cities, and mountains together so smoothly that the world appears motionless. You may never sense the ground completing this daily movement, yet every careful instrument must acknowledge it, revealing that even the firmest surface in your life is participating in a rhythm written across the solar system. The planet constantly vibrates with a low-frequency hum. Even on a day without a major earthquake, Earth never becomes seismically silent. Sensitive instruments continuously record a faint background vibration known as Earth's hum, a collection of extremely low-frequency oscillations with periods so long that human ears cannot hear them and human bodies cannot feel them. This is different from the ringing produced after a giant earthquake. A powerful rupture can strike the planet like a hammer and excite its natural modes for days or weeks, but the hum persists during seismically quiet periods, continually renewing itself without one dramatic starting event. Its strongest source appears to be the ocean. Storms generate ordinary surface waves, and when waves with different directions and periods interact, they can create much slower pressure variations. Long-period waves, known as infragravity waves, may travel across ocean basins, reach continental margins, and press rhythmically against the seafloor. That pressure transfers a tiny amount of energy into the solid planet, producing seismic waves that spread through the crust and mantle. Coastlines are especially important because approaching waves interact with shallow water, sloping seabeds, and irregular coastal geometry, creating forces that can couple efficiently with the ground. A major storm in one ocean can therefore strengthen low-frequency vibrations detected by seismic stations thousands of kilometers away. The signal is extraordinarily weak, and separating it from wind, human activity, instrument noise, local weather, and more familiar ocean-generated microseisms requires careful analysis. Yet once isolated, the hum becomes useful. Because its waves travel through Earth continuously, scientists can use ambient seismic noise to investigate underground structures without waiting for a suitable earthquake. By comparing the background vibration recorded at different stations, researchers can recover information about the paths the waves followed and create images of the crust beneath volcanoes, cities, sedimentary basins, and regions where natural earthquakes are rare. The hum also changes with seasons as storm tracks and ocean conditions shift, allowing the solid planet to carry a subtle record of weather moving across the seas. It is tempting to imagine Earth as quiet between disasters, as though the planet speaks only when a fault breaks or a volcano erupts. The instruments tell a different story. Waves are always touching shorelines, the seafloor is always receiving pressure, and the ground is always responding with motions too slow and faint for you to notice. Beneath the traffic, voices, wind, and ordinary sounds of life lies a deeper vibration with no clear beginning and no moment of complete rest. Earth is not producing a musical note in the human sense, but it is continuously resonating, turning distant storms into a planetary murmur that passes through stone while the surface world sleeps. Sea level is not the same height across the entire planet. The phrase sea level sounds like a single horizontal line wrapped evenly around Earth, but no such perfectly uniform line exists in the real ocean. When people say a location is a certain height above sea level, they are using a carefully defined reference rather than comparing it with one physically identical water height found at every coast. Local sea level is shaped by many influences acting at once. Winds can push water toward or away from shore. Atmospheric pressure can slightly depress or raise the sea surface. Currents can maintain persistent differences between neighboring regions. And temperature changes the volume of seawater as warmer water expands. Salinity also affects density, while river flow, seasonal weather, tides, and the shape of bays can change what a tide gauge records. Just as important, the land beside the water can move. A coastline may sink as groundwater is removed or sediment compacts, making the sea appear to rise faster relative to the ground. Another region may rise because the crust is still rebounding after the disappearance of an ancient ice sheet, causing local relative sea level to rise more slowly or even fall for a time. This is why a global average cannot tell every community precisely what will happen outside its harbor. Scientists distinguish between global mean sea level, which describes the average volume and height of the world's oceans, and relative sea level, which describes the water's height compared with the moving land at one particular place. Tide gauges provide long records along coastlines, while radar altimeters aboard satellites measure the distance between the spacecraft and the ocean, allowing researchers to track broad changes far from land. These measurements must be combined with information about waves, tides, atmospheric conditions, land motion, gravity, and satellite orbits before a meaningful trend emerges. Surveyors also use a gravity-defined reference surface called the geoid, representing the form a resting global ocean would approximately follow under Earth's gravity and rotation. Even this is a model, rather than a visible mark painted around the planet. The ocean is constantly moving, and its actual average surface does not perfectly coincide with the geoid everywhere. Sea level is therefore real and measurable, but it is not simple. It is an agreement between water, gravity, moving land, climate, and the reference system used to describe them. When you stand at a beach, the waterline may seem like the most natural zero point imaginable, yet another coast has its own history of currents, pressure, temperature, and vertical land motion. The seas are connected, but they do not occupy one universally identical height. What humanity calls level is a carefully calculated balance imposed on a living ocean that has never promised to remain still.